Hello there, and welcome. Tonight I want to take you somewhere peaceful, somewhere familiar yet filled with hidden wonder. I want to take you to a quiet kitchen on a calm evening, where the day has settled into stillness and the only sound is perhaps the gentle hum of a refrigerator or the soft tick of a clock on the wall. Picture yourself there with me, standing by a stove where a pot sits waiting, its metal surface cool to the touch, but about to become the stage for something quietly remarkable. Inside this pot, scattered across the bottom like tiny golden planets, in a miniature solar system, rest a handful of popcorn kernels. They lie there so still, so patient, holding secrets within their tough outer shells that connect to the fundamental laws that govern our entire universe. As we stand here together in this peaceful moment, I wonder where you might be listening from right now. Perhaps you're tucked into bed in a city where the lights twinkle outside your window like earthbound stars. Maybe you're in a small town where the night is deep and quiet, or somewhere in between, in a place that feels uniquely yours. What time is it where you are? Is it that precious hour when the world feels like it's taking a deep breath, when everything slows down and the busy noise of day finally gives way to the gentle whisper of night? If you find yourself enjoying this journey we're about to take together through the quiet physics of everyday wonders, perhaps you'd like to follow along for more of these sleepy explorations into the patterns that surround us. There's something beautiful about sharing these moments of curiosity and calm with others who appreciate the gentle mysteries hiding in plain sight. But for now, let's return to our kitchen, to our pot, to our waiting kernels, and begin to uncover why something as simple as popcorn can teach us about the elegant rules that shape everything from the smallest molecule to the largest star. The stove beneath our pot begins to warm, and already we can imagine what's happening at levels too small for our eyes to see. Heat, that most fundamental form of energy transfer, begins its patient journey upward through the metal of the pot. It's the same heat that flows from stars to planets, from warm bodies to cool air, from every higher energy state to every lower one, always seeking balance, always spreading out according to rules that never sleep and never tire. The oil in the pot, if we've added some, begins to shimmer ever so slightly, its molecules starting to move with more enthusiasm, like a calm lake beginning to sense the approach of a gentle breeze. And our kernels, those small sealed packages of potential, begin to absorb this warmth into their golden hulls. Each kernel is like a tiny universe unto itself, containing within its boundaries all the elements necessary for a transformation that seems almost magical but is entirely natural. Inside that tough outer shell, which botanists call the pericarp, lies a small amount of moisture, about 14% by weight in a good popping corn, trapped within a matrix of starch. This isn't just any starch, but a particular arrangement of complex carbohydrates that have evolved over thousands of years of corn cultivation to create something rather special. The moisture is distributed throughout the starchy endosperm, held in place by the cellular structure of the kernel, waiting for the right conditions to begin its journey from liquid to gas, from stillness to explosive movement. As the temperature rises, slowly and steadily, something profound begins to happen at the molecular level. The water molecules inside each kernel, which at room temperature move with a certain lazy contentment, begin to vibrate more vigorously. They bump into their starchy neighbours with increasing frequency and force. The long chains of starch molecules, normally rigid and tightly packed, begin to soften and become more pliable. It's a dance that's happening in every kernel simultaneously, yet each one responds in its own time, according to its own internal conditions. The exact amount of moisture it contains, the precise thickness of its hull, the particular arrangement of its starchy interior. What we're witnessing, though we cannot see it directly, is the beautiful interplay of temperature, pressure, and phase change, three of the most fundamental concepts in all of physics. Temperature, which is really just a measure of how fast molecules are moving on average, drives the entire process. As the kernels heat up, the kinetic energy of their molecules increases. This isn't random or chaotic. Despite how it might seem at the molecular level, it follows precise statistical laws that physicists have been studying for centuries, laws that govern everything from the behavior of gases in distant nebulae to the steam rising from your morning coffee. The pressure building inside each kernel is a direct consequence of the gas laws that were first discovered by scientists like Robert Boyle and Jacques Charles in the 17th and 18th centuries. These laws tell us that when you heat a gas in a confined space, its pressure must increase. It's as inevitable as gravity pulling objects toward Earth, as reliable as the sunrise. Inside our popcorn kernels, the water is beginning its transformation from liquid to vapor, and as it does, it needs more space, much more space. A single gram of water, when it becomes steam at atmospheric pressure, wants to occupy about 1700 times more volume than it did as a liquid. But our kernels won't let it. Their tough hulls hold firm, trapping the expanding vapor inside, causing the pressure to build and build. This is where popcorn becomes a perfect little demonstration of phase change, that remarkable process by which matter transforms from one state to another. We're most familiar with phase changes in water, ice melting to liquid, liquid evaporating to vapor, but they happen everywhere in nature. Stars undergo phase changes in their cores as hydrogen fuses into helium. Metals undergo phase changes as they cool from liquid to solid, their atoms arranging themselves into crystalline patterns. Even the universe itself may have undergone phase changes in its earliest moments, as the fundamental forces separated from each other in the cooling aftermath of the Big Bang. In our humble kitchen, with our simple pot and our patient kernels, we're about to witness phase change in action. But what makes popcorn particularly fascinating is that it doesn't just involve water changing from liquid to gas. The starch inside the kernel undergoes its own transformation. As it heats up in the presence of that small amount of moisture, it transitions from a hard, crystalline state to something more like a moldable plastic. Scientists call this the glass transition temperature, and it's crucial to understanding why popcorn pops the way it does. Without this transformation of the starch, we wouldn't get the light, crispy texture we associate with popcorn. Instead, we might just get a cracked kernel with some steam escaping, like what happens when you heat other types of corn that aren't meant for popping. The kitchen around us feels peaceful and timeless, but inside each kernel, time is accelerating. Molecular collisions that might happen once every few nanoseconds at room temperature are now occurring much more frequently. The water molecules are moving faster and faster, occasionally reaching speeds that allow them to break free from their liquid state and become vapor. But they have nowhere to go. The hull holds them in, and so the pressure builds. 1 atmosphere, 2 atmospheres, 3, 4, 5. The pressure inside a kernel just before it pops can reach 6 to 7 times the atmospheric pressure outside. Similar to the pressure you'd experience about 60 meters underwater. Think about that for a moment. Inside something as small and seemingly simple as a popcorn kernel, pressures are building that would crush many everyday objects. Yet the hull holds, at least for a while. This is because the pericarp of popcorn has evolved to be remarkably strong for its thickness. It's made of cellulose and other tough plant fibers arranged in a way that can withstand significant internal pressure. But everything has its breaking point, and popcorn hulls are no exception. What's remarkable is that this breaking point tends to occur at roughly the same temperature for most kernels of the same variety, usually around 180 to 190 degrees Celsius, or about 355 to 375 degrees Fahrenheit. This consistency might seem strange at first. After all, no two kernels are exactly identical. They vary in size, in shape, in the exact thickness of their hulls, in their precise moisture content. You might expect them to pop at wildly different temperatures, like a classroom full of students finishing a test at completely different times. But instead, they pop within a relatively narrow range, creating that familiar crescendo of popping sounds that starts slowly, builds to a rapid staccato, and then gradually fades back to silence. There's something almost musical about it, as if the kernels are following a score written by the laws of physics themselves. The reason for this consistency lies in the way popcorn has been selected and cultivated over thousands of years. The varieties of corn that pop well have been chosen specifically because they have the right combination of hull strength, moisture content, and starch composition. Natural selection, guided by human preference, has created a food that reliably transforms at a predictable temperature. It's a beautiful example of how human culture and natural physics can work together to create something that seems almost designed, even though it arose through gradual selection and cultivation. As we continue to watch our pot, the first wisps of steam might begin to rise from the oil, carrying with them the faint, pleasant scent of heating corn. The kernels are still quiet, still apparently unchanged, but inside them the drama is building toward its climax. The water vapor pressure is approaching that critical point, where the hull can no longer contain it. The starch has softened to just the right consistency. All the conditions are aligning for that moment of transformation that we call popping. But let's pause here for a moment and consider what we're really observing. This isn't just about snack food. This is about the fundamental way that matter and energy interact. The heat flowing into our kernels is the same kind of energy transfer that drives weather patterns, ocean currents, and the circulation of plasma in the sun. The pressure building inside each kernel follows the same laws that govern the atmosphere of planets and the interiors of stars. The phase changes occurring, water to steam, hard starch to soft foam, are the same kinds of transformations that have shaped the universe since its beginning. In this quiet kitchen, in this ordinary moment, we're connected to the cosmos in ways that might surprise us. The carbon atoms in the kernel's starch were forged in the hearts of dying stars billions of years ago. The hydrogen in their moisture was created in the first few minutes after the Big Bang. The energy heating our pot comes ultimately from the sun, that massive fusion reactor that has been steadily converting hydrogen to helium for over 4 billion years. Even the metal of our pot has a cosmic history. Its iron atoms created in supernovae, scattered across space, gathered by gravity into our planet, mined from the Earth, refined, shaped, and finally brought here to this peaceful kitchen where we stand together, waiting for the first pop. The temperature continues to rise degree by degree, and we're approaching that special threshold. Inside the kernels, the molecular dance has become frantic. Water molecules are escaping from their liquid state at an ever-increasing rate. The vapor pressure is pushing outward with tremendous force. The hull is straining, its molecular bonds stretching to their limits. We're balanced on the edge of change, in that precious moment before transformation when everything is potential, everything is possibility. This is what physicists call a critical point, a precise set of conditions where a system undergoes a dramatic change. Critical points exist everywhere in nature. Water has a critical point where the distinction between liquid and gas disappears. Magnets have a critical temperature above which they lose their magnetism. The universe itself may have passed through critical points as it cooled and expanded, each one marking a fundamental change in the nature of reality. And here in our kitchen, each kernel is approaching its own critical point, that precise combination of temperature and pressure where the hull can no longer hold and must give way. What's beautiful about this moment is its inevitability combined with its unpredictability. We know the kernels will pop. The laws of physics guarantee it. But we don't know exactly when each individual kernel will reach its breaking point. This combination of deterministic laws and statistical variation is one of the deep truths about our universe. Even when we know the rules perfectly, individual events can still surprise us. It's why weather is hard to predict beyond a few days, why quantum mechanics deals in probabilities rather than certainties, and why a pot of popcorn creates a unique pattern of pops every time, even though the underlying process is always the same. The oil in our pot has reached that critical temperature now. If we were measuring it with a thermometer, we'd see it hovering around 180 degrees Celsius. The kernels have been absorbing this heat steadily, their internal temperature rising to match their surroundings. Inside the first kernel to approach the critical point, the pressure has reached perhaps 6 or 7 atmospheres. The hull is stretched to its absolute limit. The water vapor is pressing outward with all the force that temperature and confinement can create. The starch is soft and ready to expand. Everything is poised, balanced on the knife's edge between stillness and sudden change. And then, in a moment that lasts perhaps 1/100th of a second, it happens. Somewhere on the hull, perhaps at a point slightly thinner than the rest, or where the molecular structure has a tiny imperfection, the forces become too much. A crack appears, microscopic at first but propagating at the speed of sound through the hull material. The pressurized vapor inside sees its chance and rushes toward this weakness, widening the crack, tearing the hull apart. The sudden release of pressure causes the remaining liquid water to flash into steam, expanding violently. The softened starch, no longer constrained, expands outward like a tiny explosion of foam, cooling and hardening almost instantly into the white fluffy structure we recognize as popped corn. That first pop breaks the silence of our kitchen with a sound that's both surprising and expected. It's a small percussion in the quiet night, a tiny cymbal crash in the symphony of physics. The kernel is transformed completely in less time than it takes to blink, turning itself inside out, increasing its volume by 40 or 50 times, changing from a hard seed to an edible cloud. It's a kind of everyday magic that we've witnessed countless times, yet when we really think about what's happening, the forces involved, the transformations taking place, the perfect timing of multiple physical processes, it remains genuinely wondrous. But our first kernel was just the beginning. Now others are reaching their critical points too. The second pop comes perhaps a second later, then another, then two almost simultaneously. The rhythm begins to build, like raindrops starting to fall at the beginning of a shower. Each pop is an individual event, a single kernel reaching its unique breaking point, but together they create a pattern, a cascade of transformations that seems orchestrated even though each kernel knows nothing of its neighbours. This is emergence, the way complex patterns arise from simple rules repeated many times. It's the same principle that creates the murmuration of starlings, the formation of snowflakes, the spiral of galaxies. No single kernel decides when to pop based on what the others are doing, yet they create a collective behaviour that has rhythm and pattern. The popping starts slowly because only a few kernels have the exact right combination of factors to pop at the lowest temperatures. As the temperature rises slightly higher, more kernels reach their thresholds, and the popping accelerates. Eventually, most of the viable kernels have popped, and the rate slows again, leaving us with just occasional late bloomers, and, inevitably, a few kernels that never pop at all. Those unpopped kernels at the bottom of our pot, the ones we sometimes call old maids or spinsters, in a terminology that reflects outdated social concepts, are not failures so much as variations. Perhaps their hulls were too thick, requiring a higher pressure than could be achieved before the moisture escaped through some tiny pore. Perhaps they had too little moisture to begin with, or a leak in their hull that prevented pressure from building. Or perhaps their starch wasn't quite the right composition to undergo the necessary transformation. They remind us that even in processes governed by precise physical laws, individual variation persists. Not every seed grows, not every star forms planets, not every kernel pops. This variation isn't a flaw in the system. It's a fundamental feature of a universe where probability and statistics play essential roles. As we watch and listen to our pot of popping corn, we can appreciate the deep connections between this simple culinary event and the broader workings of our universe. The conservation of energy ensures that the heat from our stove becomes the kinetic energy of expanding steam and flying kernel hulls. The conservation of mass means that every atom that was in the unpopped kernels is still there in the popped corn, just rearranged into a new configuration. The second law of thermodynamics drives the heat flow from the hot oil to the cooler kernels and governs the irreversible nature of the popping. You can't unpop popcorn any more than you can unmix cream from coffee, or reverse the flow of time. The entropy of our system has increased dramatically. Where once we had organised compact kernels with water and starch neatly contained, we now have a chaotic pile of expanded, irregular shapes with their contents exposed to the world. This increase in entropy, this movement from order to disorder, is the same force that drives all spontaneous processes in our universe. It's why ice melts, why perfume spreads through a room, why stars eventually burn out, and why time seems to flow in only one direction. Our popping corn is a tiny example of the universe's inexorable trend toward increasing entropy, yet it results in something we find delightful rather than depressing. The sound of popping has reached its crescendo now, a cheerful cacophony of small explosions that fills our quiet kitchen with life and energy. Each pop sends a kernel flying upward, sometimes hitting the lid of our pot with a metallic ping, sometimes landing back in the oil with a soft splash. The violence of each individual pop, remember, we're talking about pressures of several atmospheres being released in hundredths of a second, is transformed by repetition and context into something pleasant and appetizing. It's a reminder that perspective matters in physics as much as in life. What seems chaotic at one scale can seem ordered at another. What appears violent in slow motion can seem gentle at normal speed. The smell filling our kitchen now is distinctive and comforting. It's the smell of toasted starch, of caramelizing sugars, of hot oil and transformed grain. These are Maillard reactions, the same chemical processes that brown bread, roast coffee and sear meat. They're happening because our popped corn, having expelled much of its moisture, can now reach temperatures above the boiling point of water. The surface of the popped kernels is browning slightly, developing hundreds of different flavour compounds that our noses detect as that characteristic popcorn aroma. Chemistry and physics are working together to create not just a transformation of structure, but a transformation of flavour and scent. As the popping begins to slow, with longer gaps between each pop, we're witnessing the tail end of a statistical distribution. Most kernels that we're going to pop have already done, so the temperature is still high enough, but we're running out of viable candidates. It's like watching the last few radioactive atoms in a sample decay, or the last few people leaving a party. The process that seemed so vigorous just moments ago is winding down, following a predictable curve that statisticians call a normal distribution or bell curve. The same mathematical pattern appears everywhere in nature, in the heights of people, the velocities of molecules in a gas, the brightness of stars, and yes, the timing of popping corn. This brings us to a profound realization. The simple question we started with, why does popcorn pop at around the same temperature, has led us through a journey that touches on some of the deepest principles in physics. We've encountered thermodynamics and statistical mechanics, phase transitions and critical points, emergence and entropy. We've seen how cultivation and evolution have fine-tuned a natural process to serve human purposes. We've witnessed the transformation of matter and energy in real time, governed by laws that operate from the quantum scale to the cosmic scale. Yet for all this complexity, for all these interconnections with fundamental physics, popcorn remains wonderfully accessible and familiar. You don't need to understand gas laws to enjoy the sound of kernels popping. You don't need to know about phase transitions to appreciate the texture of the well-popped corn. The physics enriches our appreciation, but doesn't gatekeep our enjoyment. This is one of the beautiful things about the physical world. It operates perfectly well whether we understand it or not, yet rewards our curiosity when we choose to look deeper. The last few pops are coming now, separated by several seconds of quiet. Each one seems more precious because of its rarity, like the last notes of a song or the final words of a bedtime story. Our pot of kernels has transformed from potential to actual, from seed to food, from order to delicious chaos. The heat is still flowing, the oil is still shimmering, but the drama of transformation is nearly complete. We're left with a pot full of popped corn, each piece unique in its shape but united in its origin and transformation. As we prepare to turn off the heat, and perhaps add some salt or butter to our creation, we can carry with us the wonder of what we've witnessed. In this ordinary kitchen, on this quiet evening, we've seen the laws of physics play out in miniature. We've watched matter change state, energy flow and transform, and order give way to entropy. We've heard the sound of molecular bonds breaking, and seen the result of millions of years of evolution and thousands of years of cultivation. We've participated in a process that connects us to the cosmos and to our ancestors who first discovered that certain kernels of corn would transform when heated. The popcorn sits before us now, cooling slightly, the last wisps of steam rising and disappearing into the kitchen air. Each popped kernel is like a small white flower, unique in its particular pattern of expansion but recognizable as part of a family. Some are perfectly mushroomed, others more butterfly-shaped. Some are compact and round, others wild and irregular. This variation within unity is another echo of the patterns we see throughout nature. Snowflakes that are all hexagonal but each unique. Humans who share the same basic structure but each with individual features. Stars that all burn hydrogen but each with its own particular characteristics. The first pop has broken the silence, that singular percussion that announces the beginning of transformation, and now we stand at the edge of understanding something truly remarkable about the nature of collective behaviour in physical systems. That first kernel, brave pioneer that it was, has opened the door for its companions, though not through any form of communication or coordination that we might recognise. Instead, what we're about to witness is a beautiful example of how individual objects following the same physical laws can create patterns that seem orchestrated, seem intentional, seem almost like a conscious decision to act together. The second pop comes now, perhaps a heartbeat or two after the first, and then another follows, and suddenly we're hearing not isolated events, but the beginning of a rhythm, a cascade, a symphony of small explosions that fill our quiet kitchen with their cheerful violence. Let's think about this mystery for a moment. really consider what seems strange about it. Each kernel in our pot is a separate entity, enclosed in its own hull, containing its own moisture, experiencing its own particular journey from cold to hot. Some kernels are larger, some smaller. Some have thicker hulls, others thinner. Some started with 15% moisture, others with 13%. Some are sitting directly on the bottom of the pot where the heat is most intense. Others are nestled on top of their companions, receiving their heat second-hand. Given all these variations, all these differences, wouldn't you expect the popping to be completely random, scattered across a wide range of temperatures like raindrops falling on a vast plain? But that's not what happens, and this is where our mystery deepens into something genuinely fascinating about the nature of physical systems. Instead of chaos, we get a pattern. Instead of randomness, we get a kind of order. The kernels don't pop at wildly different temperatures spread across 100 degrees. They cluster their transformations within a narrow band, roughly between 175 and 190 degrees Celsius for most varieties of popping corn, with the peak of activity happening right around 180 to 185 degrees. It's as if they've agreed on a meeting time, as if they've coordinated their actions, as if they're following some secret plan that we're not privy to. This apparent coordination becomes even more mysterious when we realize that the kernels have no way to communicate with each other. They're not sending signals through the oil, they're not releasing pheromones or chemical messages, they're not connected by any network we can detect. Each kernel is isolated in its own experience, aware only of its own internal state, responding only to its own temperature and pressure. Yet somehow, mysteriously, beautifully, they create this collective behavior that has pattern and predictability. The popping starts slowly, builds to a crescendo, and then tapers off, following the same general curve every time we make popcorn, whether it's in a pot on the stove, in a microwave, or in a commercial popping machine at a movie theatre. To understand this mystery, we need to think about what's really happening at the molecular level inside each kernel as the temperature rises. The water molecules trapped within the starchy matrix are not just getting warmer, they're getting more energetic, more violent in their movements, more desperate to escape their confinement. At room temperature, these water molecules move with an average speed of about 590 meters per second, already impressively fast, but not fast enough to overcome the attractive forces holding them in the liquid state. As the temperature rises toward 100 degrees Celsius, their average speed increases, and more importantly, the distribution of speeds widens. Some molecules are moving much faster than average, occasionally fast enough to escape the liquid and become vapor. But here's where popcorn differs from a pot of boiling water. In an open pot, water molecules that gain enough energy can simply escape into the air, which is why water evaporates even at temperatures well below boiling. But inside a popcorn kernel, there's nowhere for the vapor to go. The tough hull traps it, contains it, forces it to build up pressure. This is crucial to understanding why popcorn pops at a consistent temperature. It's not just about reaching a temperature where water wants to become steam. That happens at 100 degrees Celsius at normal atmospheric pressure. It's about reaching a temperature where the pressure of the trapped steam becomes too much for the hull to contain. The relationship between temperature and pressure in our trapped water vapor follows what physicists call the Clausius-Clapeyron equation, a mathematical relationship that describes how the vapor pressure of a substance changes with temperature. It's not a linear relationship. The pressure doesn't just increase steadily with temperature. Instead, it increases exponentially, slowly at first and then more and more rapidly. At 100 degrees Celsius, water vapor at equilibrium with liquid water has a pressure of 1 atmosphere. At 120 degrees, it's about 2 atmospheres. At 140 degrees, it's nearly 4 atmospheres. By the time we reach 180 degrees, where most popcorn pops, the vapor pressure would be about 10 atmospheres if the water could reach equilibrium with its vapor. But equilibrium is exactly what we don't have inside a popcorn kernel. The water is trying to become vapor faster than vapor can escape through any tiny pores in the hull. The pressure builds and builds, but it's not just water vapor pressure we need to consider. The air that was already inside the kernel is also expanding as it heats up, following Gay-Lussac's law, which tells us that the pressure of a gas is directly proportional to its absolute temperature if the volume is held constant. So we have water turning to steam, existing air expanding and nowhere for any of it to go. The hull holds firm, but it can't hold forever. The strength of the hull is remarkable when you think about it. These kernels, each no bigger than a pea, are containing pressures that would be dangerous in many industrial applications. The hull, made primarily of cellulose fibers arranged in a tough cross-linked pattern, is essentially a natural pressure vessel. But like all materials, it has its limits. When the stress on the hull exceeds its ultimate tensile strength, it fails. And because the hulls of cultivated popcorn have been selected over generations to have similar thickness and strength, they tend to fail at similar pressures, which are reached at similar temperatures. This is the key to understanding why kernels pop together. They're not actually coordinating their actions, they're simply reaching the same physical threshold at approximately the same time, because they're fundamentally similar in their construction. It's like having a room full of identical balloons being inflated at the same rate. They'll all pop at approximately the same pressure, not because they're communicating, but because they're made of the same material with the same strength. The variation we do see, why some kernels pop a bit earlier and others a bit later, comes from the small differences between individual kernels. One might have 14% moisture while another has 13%. One might have a hull that's 5% thicker than average. One might have a tiny imperfection that makes it slightly weaker. These small variations follow what statisticians call a normal distribution, the famous bell curve that appears everywhere in nature when you have many small random factors contributing to an outcome. The thickness of hulls varies randomly around an average value. The moisture content varies randomly around an average value. The exact temperature each kernel experiences varies slightly based on its position in the pot. When you combine all these small random variations, you get a distribution of popping times that clusters around an average, with fewer kernels popping at the extremes. This is why the popping starts slowly. Only the kernels at the low end of the distribution, those with the perfect combination of factors for early popping, go first. Then as the temperature rises, more and more kernels reach their threshold, and the popping accelerates. Finally, only the kernels at the high end of the distribution remain, those that need extra heat or pressure to pop, and the rate slows again. But there's another layer to this mystery that makes it even more interesting. The kernels aren't just passive recipients of heat, they're active participants in their own transformation. As each kernel heats up, the starch inside undergoes its own changes. At around 65 degrees Celsius, the starch begins to gelatinize in the presence of the moisture, becoming softer and more pliable. This is essential for good popping. If the starch remained hard and crystalline, the kernel would simply crack and release its steam, without expanding into the fluffy shape we associate with popcorn. The gelatinization temperature of starch is relatively consistent, adding another constraint that helps synchronize the popping. Furthermore, the starch needs to reach what food scientists call the glass transition temperature, the point where it changes from a hard, glassy state to a soft, rubbery state. For the starch in popcorn with its small amount of moisture, this happens around 170 degrees Celsius. Below this temperature, even if the pressure inside the kernel were high enough to crack the hull, the starch wouldn't expand properly, it would be too rigid, too brittle. But once it passes the glass transition temperature, the starch becomes capable of expanding rapidly when the pressure is released, like a compressed spring suddenly set free. So we have multiple processes all needing to align for successful popping. The water needs to generate enough vapor pressure, the hull needs to reach its breaking point, and the starch needs to be in the right state to expand. It's like a combination lock where all the tumblers need to line up for the lock to open. And because these processes are all temperature dependent and happen at similar temperatures in most kernels, they create a narrow window where popping is most likely to occur. This is why popcorn pops around the same temperature, not because of any mysterious coordination, but because of the beautiful convergence of multiple physical processes. The sound of popping fills our kitchen now with increasing frequency, each pop a small report of another kernel reaching its critical point and undergoing its violent transformation. If we could see inside the pot in slow motion, we would witness something truly spectacular. As each hull fails, it doesn't just crack, it tears apart violently, typically splitting along its weakest point and peeling back like a tiny explosive flower. The superheated water inside, suddenly released from pressure, flashes into steam so quickly that it's almost instantaneous. This rapid expansion of steam drives the soft gelatinized starch outward, inflating it like a balloon but much, much faster. The starch foam expands to many times its original volume in just a few milliseconds, then cools and hardens almost immediately into the familiar shape of popped corn. The violence of this transformation is hard to appreciate at normal speed. High-speed cameras have revealed that the kernel can experience accelerations of up to 200 times gravity as it pops, spinning and flying through the air. The expanding starch can reach speeds of several meters per second. The temperature of the steam escaping can be well over 200 degrees Celsius. Yet all of this happens so quickly that to our eyes and ears, it's just a simple pop and jump. It's a reminder that timescale matters in physics. What seems gentle and amusing at one time, scale can be violent and dramatic at another. The pattern of popping we're hearing now, that characteristic acceleration from slow to fast and back to slow, tells us something profound about how nature works. This isn't unique to popcorn. The same pattern appears in many natural processes where individual events cluster around some average value. Radioactive decay follows this pattern, with atoms most likely to decay at a characteristic half-life. Chemical reactions follow this pattern, with molecules most likely to react at a characteristic temperature. Even human behaviors often follow this pattern. The times people arrive at work, the ages at which children learn to walk, the speeds cars travel on a highway. It's a signature of systems where many independent actors are responding to similar conditions. What's particularly beautiful about the popcorn version of this pattern is how accessible it makes these deep statistical principles. You don't need a particle accelerator or a sophisticated laboratory to observe the bell curve in action. You just need a pot, some heat, and a handful of kernels. Every time you make popcorn, you're conducting a physics experiment that demonstrates fundamental principles about how the universe works. You're watching entropy increase, energy transform, and matter change state. You're observing statistical mechanics and thermodynamics in real time. You're witnessing the same kinds of processes that occur in stars, in clouds, in living cells, and in the quantum realm. The rhythm of popping has reached its peak now, a cheerful cacophony that fills the kitchen with sound and motion. Kernels are transforming so quickly that their individual pops merge into a continuous rustle and rattle. The lid of our pot, if we have one, dances with the impact of flying kernels. The smell of toasting corn grows stronger, mixing with the scent of hot oil to create that distinctive aroma that signals movie theatres and carnival midways and cozy evenings at home. This is the moment of maximum transformation, when the rate of change is highest, when the system is most dynamic and energetic. Yet even in this apparent chaos, there's order. If we were counting the pops per second and plotting them on a graph, we would see a smooth curve emerging from the noise. Individual kernels might pop randomly, but collectively they follow a predictable pattern. This is the magic of large numbers, the way that randomness at small scales gives rise to predictability at large scales. It's why insurance companies can predict how many claims they'll receive even though they can't predict which specific customers will file claims. It's why gas laws work, even though we can't track individual molecules. It's why popcorn pops reliably around the same temperature, even though each kernel is unique. The mystery of why kernels pop together also connects to a broader principle in physics called universality. This is the idea that many different systems, despite their different microscopic details, can show the same large-scale behavior near critical points. The way water turns to steam, the way magnets lose their magnetism, the way materials undergo phase transitions. These all show similar mathematical patterns near their critical points. Popcorn popping is another example of this universality. Despite the complex biology of corn kernels, despite the intricate chemistry of starch and water, the popping follows the same statistical patterns we see in much simpler physical systems. As the popping begins to slow, with longer gaps between each pop, we can appreciate another aspect of this collective behavior. The kernels that pop later aren't necessarily defective or fundamentally different. They might just need a slightly higher temperature, or a bit more time for heat to penetrate to their centers, or they might have started with slightly less moisture and need to concentrate what they have to build sufficient pressure. They're the late bloomers, the ones at the tail end of the distribution. In any collection of similar objects undergoing the same process, there will always be early adopters and late arrivals, pioneers and stragglers. This variation isn't a flaw, it's a fundamental feature of nature. The spaces between pops are growing longer now, giving us time to appreciate each individual transformation. That kernel that just popped, it waited through all the chaos, building its internal pressure slowly and steadily, until finally it couldn't hold any longer, and that one just now, perhaps it was nestled in a cooler spot, taking longer to reach the critical temperature. Each late-popping kernel has its own story, its own particular combination of factors that placed it at the high end of the distribution. They remind us that even in systems governed by statistical laws, individuals still matter. Each kernel's pop is unique, even as it contributes to the predictable whole. We should also consider the kernels that will never pop, the ones that will remain at the bottom of our pot no matter how long we heat them. These aren't failures in any moral sense. They're simply kernels whose physical parameters place them outside the range where popping is possible. Perhaps their hulls are too thick or too porous. Perhaps they've lost too much moisture during storage. Perhaps they have some structural defect that prevents pressure from building. They're part of the distribution too, the far tail that extends beyond the popping threshold. In industrial popcorn production, these unpopped kernels are actually valuable for quality control. Too many suggest the corn is too dry or damaged. Too few might mean the kernels aren't being heated enough for maximum yield. The phenomenon we're observing, this tendency for kernels to pop around the same temperature, has practical implications beyond our kitchen. It's why popcorn machines can be designed with standard operating temperatures. It's why microwave popcorn bags can be engineered to pop most kernels without burning them. It's why movie theaters can train teenagers to make consistent popcorn with simple procedures. The predictability that emerges from the underlying physics makes popcorn a reliable, commercializable product. If kernels popped at wildly different temperatures, popcorn as we know it might not exist as a popular snack food. This clustering of popping around a characteristic temperature also connects to ideas in evolution and optimization. Over thousands of years of cultivation, humans have selected corn varieties that pop well, and popping well includes popping at a consistent, predictable temperature. Varieties where kernels popped across too wide a temperature range would have been harder to prepare properly. Some kernels would burn while others remained unpopped. Natural variation provided the raw material, human selection provided the direction, and physics provided the constraints. The result is a food product that's been optimized through a collaboration between human culture and natural law. The last few pops are coming now, separated by several seconds of anticipation. Each one seems more precious because of its rarity, more noticeable because of the quiet that surrounds it. These final kernels have finally reached their thresholds, finally built enough pressure, finally achieved the conditions necessary for transformation. They're like the last guests arriving at a party, the last flowers blooming in spring, the last stars forming in a galaxy. They complete the pattern, finish the process, bring closure to the event we've been witnessing. As we prepare to remove our pot from the heat, we can reflect on what we've learned about this mystery. The kernels don't really pop together in the sense of coordinating their actions. Instead, they pop at around the same temperature, because they're all following the same physical laws with similar starting conditions. The apparent coordination is an emergent property, arising from the statistics of many similar objects undergoing the same process. It's a beautiful example of how order can arise from disorder, how patterns can emerge from randomness, how the simple rules of physics can create complex and seemingly purposeful behaviors. The silence that follows the last pop is profound in its own way. The transformation is complete. What began as hard, dense kernels has become light, airy, popped corn. What started as potential energy stored in molecular bonds and trapped moisture has been released as kinetic energy, sound, and heat. What was ordered has become disordered. What was compressed has expanded. What was hidden has been revealed. The pot before us now contains the evidence of hundreds of individual phase transitions, each one following the same laws but expressing them in its own unique way. Let us now journey from our comfortable kitchen into the realm of scientific investigation, where researchers have spent decades trying to understand exactly what happens in that fraction of a second when a kernel transforms. Picture, if you will, a different kind of kitchen, a laboratory where every variable can be controlled, every measurement precisely taken, every pop carefully observed and recorded. Here, scientists approach popcorn not as a snack, but as a fascinating example of physical processes in action, a model system for understanding rapid phase transitions and explosive expansions. The tools they use range from simple thermometers to high-speed cameras capable of capturing tens of thousands of frames per second, from pressure sensors smaller than rice grains to acoustic equipment that can analyze the precise frequency spectrum of a popping kernel. the history of scientifically studying popcorn goes back further than you might expect. As early as the 1940s, researchers were trying to understand what made some corn varieties pop better than others. They discovered that moisture content was critical, too little, and the kernels wouldn't generate enough pressure to pop properly, too much, and the hull would leak or weaken before sufficient pressure could build. Through careful experimentation, they found that the optimal moisture content was around 13.5 to 14.5% by weight. This might seem like a narrow range, but it represents a delicate balance. Below 13%, many kernels fail to pop at all. Above 15%, the popped corn tends to be tough and chewy rather than light and crispy. These early researchers also discovered something surprising about the temperature of popping. Using oil baths held at precise temperatures, they found that most kernels wouldn't pop at all below about 175 degrees Celsius, regardless of how long they were heated. Above 180 degrees, the popping rate increased dramatically, reaching a maximum around 185 to 190 degrees. But if the temperature was raised much higher, above 200 degrees, the kernels would pop so violently that they often shattered into small pieces rather than expanding into the familiar butterfly or mushroom shapes. This temperature window, roughly 175 to 190 degrees Celsius, has remained remarkably consistent across different varieties of popping corn, suggesting that it's determined by fundamental physical properties rather than superficial characteristics. Modern research has given us even more detailed insights into the popping process, using microthermocouples, tiny temperature sensors that can be inserted into individual kernels. Scientists have tracked the internal temperature of kernels as they heat up. They found that the center of a kernel can lag behind the surface temperature by several degrees, especially in larger kernels or when heating is rapid. This temperature gradient means that different parts of the kernel might be experiencing different conditions at the moment of popping, adding another layer of complexity to the process. The hull typically reaches the critical temperature first, while the center might still be several degrees cooler. This gradient could explain why some kernels pop incompletely, with only part of the starch expanding while the rest remains dense. High-speed photography has revealed details about popping that are impossible to see with the naked eye. French researchers in 2015 used cameras recording at 5,000 frames per second to study exactly how kernels pop. They discovered that the process happens in distinct stages. First, a crack appears in the hull, usually starting at the tip of the kernel where the hull is often thinnest. This crack propagates around the kernel in about 2 milliseconds, faster than the blink of an eye. Then comes the explosive expansion as the superheated moisture flashes to steam and the softened starch is driven outward. The entire kernel can invert itself, turning inside out like a sock being pulled off a foot. The researchers found that kernels don't just pop, they jump, sometimes reaching heights of several inches as the rapid expansion of steam creates a tiny rocket effect. Even more remarkably, these high-speed studies revealed that popping kernels often rotate rapidly, spinning at rates up to 500 revolutions per second. This rotation comes from the asymmetric release of steam. The crack doesn't open uniformly, so the escaping vapor creates a torque that sets the kernel spinning. It's like a tiny steam turbine, converting the thermal energy of the hot kernel into rotational kinetic energy. This spinning motion helps explain why popped kernels end up with such varied and irregular shapes. The centrifugal force from the rotation affects how the expanding starch solidifies, creating the wings and protrusions that give each piece of popcorn its unique character. Pressure measurements have provided crucial data about the forces involved in popping. Researchers have used tiny pressure transducers, devices that can measure pressure changes, placed inside specially prepared kernels. These experiments are technically challenging. The sensor must be small enough to fit inside a kernel without significantly affecting its popping behavior, yet robust enough to survive the violent conditions during popping. The data from these experiments confirms what theory predicted. Pressures inside kernels just before popping typically reach 6 to 10 atmospheres, or about 90 to 145 pounds per square inch. That's comparable to the pressure in a bicycle tire or at the bottom of a 60-meter deep swimming pool. What's particularly interesting about these pressure measurements is how quickly the pressure releases when the hull fails. The pressure drops from several atmospheres to ambient pressure in less than a millisecond. This rapid decompression is what drives the explosive expansion of the starch. If the pressure released more slowly, say, through a small leak rather than a catastrophic failure, the starch wouldn't expand properly. This is why kernels with damaged hulls often fail to pop correctly. They can't build up enough pressure, or the pressure leaks out too slowly to create the rapid expansion needed for proper popping. Acoustic analysis has revealed that the sound of a popping kernel contains a wealth of information about the popping process. The pop isn't just a single sound, but a complex mixture of frequencies that can tell us about the size of the kernel, the violence of the expansion, and even the final shape of the popped corn. Researchers have found that the fundamental frequency of the pop, the lowest and usually loudest component, typically falls between 1000 and 3000 Hz, right in the range where human hearing is most sensitive. This might not be a coincidence. Corn that popped with a satisfying sound might have been preferentially selected during domestication. The acoustic signature also includes higher frequency components created by the tearing of the hull and the turbulent expansion of steam, giving each pop its unique character. Studies of the material properties of popcorn hulls have revealed why they're so well suited for their role. The pericarp consists of several layers of dead cells filled with cellulose and hemicellulose fibers. These fibers are arranged in a cross-hatched pattern that gives the hull remarkable strength for its thickness. Measurements show that the hull can withstand tensile stresses of up to 10 megapascals, about 100 times atmospheric pressure, before failing. But the hull isn't uniformly strong. There are often weak points, particularly at the tip where the kernel was attached to the cob, and it's usually at these weak points that failure begins. This is actually beneficial for good popping. If the hull were uniformly strong, it might shatter into many pieces rather than splitting open cleanly. The role of starch in popping has been extensively studied using techniques like differential scanning calorimetry, which measures how materials absorb or release heat as they undergo phase transitions. These studies show that the starch in popcorn undergoes several transitions as it heats up. First, around 65 degrees Celsius, it begins to gelatinize in the presence of moisture, losing its crystalline structure and becoming more amorphous. Then, around 170 degrees Celsius, it undergoes the glass transition, changing from a hard, brittle state to a soft, pliable state. Finally, during the actual pop, it expands into a foam and then rapidly cools and solidifies into the crispy structure we recognize as popped corn. Each of these transitions is essential for proper popping, and they all need to occur in the right sequence and at the right rates. Research into the genetics of popcorn has identified specific genes that affect popping quality. Some genes control the thickness and composition of the hull, others affect the structure and composition of the starch, and still others influence how the kernel accumulates and retains moisture. This genetic research has allowed breeders to develop new varieties of popcorn with improved popping characteristics, kernels that pop more completely, expand to larger volumes, or have more tender textures. It's a reminder that even something as seemingly simple as popcorn is the product of complex interactions between multiple genes, each contributing to the final phenotype. But for all that we've learned through careful measurement and observation, there's still much we don't fully understand about popcorn. For instance, why do some kernels pop into butterfly shapes while others form mushroom shapes? Both types can come from the same batch of corn, popped under identical conditions. Current speculation suggests it might have to do with how the hull fails. A single clean crack might lead to a mushroom shape, while multiple cracks or irregular tearing might create butterfly shapes. But this is still being investigated, and the full answer might involve subtle differences in kernel geometry, hull structure, or starch properties that we haven't yet learned to measure. Another area of ongoing research and speculation concerns the exact mechanism of starch expansion. We know that the rapid pressure release causes the superheated water to flash to steam, and this steam expansion drives the starch outward. But the details of how the starch forms its foam structure, with hundreds of tiny air pockets separated by thin walls of solidified starch, aren't fully understood. Some researchers think the foam structure forms through a process similar to spinodal decomposition, where a homogeneous mixture spontaneously separates into distinct phases. Others suggest it's more like the formation of soap bubbles, with the expanding steam creating bubbles that are stabilized by the gelatinized starch. The truth might involve elements of both mechanisms or something else entirely. There's also speculation about whether the popping process could be optimized further. Could we breed or engineer corn that pops at lower temperatures, saving energy? Could we create kernels that pop more uniformly, reducing the number of unpopped kernels? Could we develop corn that pops into specific shapes for different applications? Some researchers are exploring these possibilities using both traditional breeding and modern genetic techniques. Others are looking at physical modifications, coating kernels with materials that might affect heat transfer or pressure, build-up, or treating them with enzymes that modify the starch structure. The study of popcorn has also led to insights that extend beyond snack food. The rapid expansion of starch during popping is similar to processes used in making expanded snacks, breakfast cereals, and biodegradable packing materials. Understanding how popcorn pops has helped food scientists develop new products and improve existing ones. The pressure buildup and sudden release in popcorn is analogous to volcanic eruptions, where dissolved gases in magma suddenly expand as pressure decreases. Some researchers have even used popcorn as a model system for studying these geological processes, since it's much safer and easier to study popping corn than erupting volcanoes. Environmental factors affecting popping have also been subjects of scientific investigation. Humidity during storage can dramatically affect popping quality, as kernels can gain or lose moisture through their hulls over time. Temperature cycling during storage can cause moisture to migrate within kernels, potentially creating gradients that affect popping. Even the altitude at which popcorn is popped matters. At higher elevations where atmospheric pressure is lower, water boils at a lower temperature, which can affect how kernels pop. Some high-altitude popcorn enthusiasts have reported that they need to adjust their popping techniques to get optimal results, though systematic studies of this effect are limited. Recent research has also looked at the nutritional changes that occur during popping. The high temperatures involved in popping can destroy some heat-sensitive vitamins, but they can also make other nutrients more bioavailable. The expansion process dramatically increases the surface area of the starch, which might affect how quickly it's digested. Some studies suggest that popped corn has a lower glycemic index than cornmeal made from the same kernels, possibly because the physical structure of popped corn affects how enzymes access the starch. These nutritional considerations add another dimension to our understanding of popcorn, connecting the physics of popping to human health and nutrition. The economics of popping quality has driven much of the research into popcorn. In commercial settings, the expansion ratio, how much the volume increases during popping, directly affects profitability. A higher expansion ratio means more popped corn from the same weight of kernels, which means higher profits for movie theaters and other vendors. This has led to extensive research into factors affecting expansion ratio, from the obvious ones like moisture content and temperature, to subtle ones like the rate of heating and the composition of the popping oil. Some studies have found that certain oils produce better expansion than others, possibly because they affect heat transfer or interact with the hull in ways that influence when and how it fails. As we stand in our kitchen, listening to the last kernels pop, we can appreciate how much scientific effort has gone into understanding this seemingly simple process. Every pop we hear has been the subject of careful study, precise measurement, and thoughtful analysis. Scientists have peered inside kernels with X-rays and MRI machines, watched them pop with high-speed cameras and thermal imaging, measured their pressure with tiny sensors and their temperature with microscopic thermocouples. They've analysed the genetics of popcorn, the chemistry of starch, the physics of pressure vessels, and the acoustics of small explosions. Yet for all this scientific scrutiny, popcorn retains its element of mystery and wonder. We can measure the temperature and pressure, we can slow down the process with high-speed cameras, we can analyse the sound and study the structure, but there's still something magical about the transformation from seed to snack. Each kernel that pops is following laws of physics that we understand quite well, yet the collective behaviour of a pot full of popping corn still feels surprising and delightful. This is perhaps the best kind of scientific understanding, detailed enough to satisfy our curiosity, but not so complete that it eliminates all mystery. The gentle chaos of popping corn that fills our kitchen is not an isolated phenomenon, not some quirky exception to the normal rules of physics, but rather a perfect miniature demonstration of the same fundamental laws that govern everything from the formation of clouds to the operation of power plants, from the breathing of our lungs to the birth of stars. As we stand here, perhaps adding a sprinkle of salt to our freshly popped corn, we're witnessing the same principles of thermodynamics, the same behaviours of matter under pressure, the same transitions between phases that shape our entire universe. The popcorn is a teacher, if we're willing to learn, offering lessons about energy, entropy, equilibrium, and the elegant mathematical relationships that describe how matter and energy interact. Consider for a moment the simple fact that heat flows from the hot stove to the cooler kernels. This seems so obvious that we rarely stop to think about it, but it represents one of the most fundamental laws of thermodynamics. Heat always flows from hot to cold, never the reverse, at least not without doing work to make it happen. This is the second law of thermodynamics in action, the same law that tells us why ice cubes melt in warm drinks, why engines need cooling systems, why the universe itself is slowly cooling as it expands. The heat flowing into our kernels is following the same rule that governs heat flow in the sun's core, in the Earth's mantle, in the mitochondria of our cells. It's a universal principle, as true for popcorn as it is for galaxies. The pressure building inside each kernel before it pops is a beautiful demonstration of Gay-Lussac's law, one of the gas laws that describes how pressure and temperature are related when volume is constant. As the temperature inside the kernel rises, the pressure must rise proportionally. This isn't a suggestion or a tendency, it's a mathematical certainty, as reliable as 2 + 2 = 4. The same law governs the pressure in car tires on a hot day, the operation of pressure cookers, the atmosphere of planets, and the interior of stars. When we watch popcorn pop, we're seeing the same physics that creates the solar wind, drives volcanic eruptions, and makes hot air balloons float. The phase change from liquid water to steam inside each kernel connects our kitchen to every other place in the universe where matter changes state. Phase changes are everywhere. Ice forming on winter windows, metals solidifying in foundries, hydrogen becoming metallic in the cores of giant planets, neutron stars crystallizing as they cool. The energy required to change water from liquid to gas, the latent heat of vaporization, is the same whether it's happening in a popcorn kernel, in a cloud forming over the ocean, or in a comet approaching the sun. It takes exactly 2,260 kilojoules to convert 1 kilogram of water at 100 degrees Celsius to steam at the same temperature, whether that water is in a laboratory beaker or inside a kernel of corn. The way popcorn demonstrates these physical laws makes them accessible and tangible in a way that textbook equations never quite achieve. When we learn about pressure and temperature and phase changes in school, they can seem abstract, disconnected from daily experience. But popcorn brings these concepts into our kitchen, makes them edible, turns them into something we can hear and smell and taste. Every kernel that pops is a successful experiment in applied physics, a demonstration that these laws really work, that they're not just theoretical constructs but practical descriptions of how the world actually operates. The expansion of the starch during popping illustrates another fundamental principle, the tendency of compressed gases to expand when pressure is released. This is how aerosol cans work, how scuba regulators deliver air to divers, how natural gas flows through pipelines to our homes. It's also how rocket engines generate thrust, how volcanoes erupt, how speech is produced in our throats. The rapid expansion of steam that drives the starch outward in a popping kernel is a tiny version of the same process that drives steam turbines in power plants, providing electricity to millions of homes. The energy that was stored as pressure inside the kernel is converted to kinetic energy of the expanding starch, just as pressure energy in steam is converted to rotational energy in a turbine. The fact that popcorn pops at a consistent temperature speaks to the statistical nature of physical laws. While individual kernels might pop at slightly different temperatures, the average behavior is predictable. This is the essence of statistical mechanics, the bridge between the random motions of individual molecules and the predictable behavior of bulk matter. It's why we can have gas laws even though we can't track every molecule, why we can predict the weather a few days ahead even though we can't follow every air molecule, why thermodynamics works even though it deals with systems containing trillions upon trillions of particles. Popcorn demonstrates that predictability can emerge from randomness, that order can arise from chaos, that simple rules applied many times can create complex but reliable patterns. The energy transformations involved in making popcorn illustrate the first law of thermodynamics. Energy cannot be created or destroyed, only converted from one form to another. The chemical energy in the gas or electricity powering our stove becomes thermal energy in the heating element. This thermal energy flows into the pot and then into the oil and kernels. Some of it goes into raising the temperature of the kernels, some into converting water to steam, some into breaking the molecular bonds in the hull when it ruptures, some into the kinetic energy of flying kernel pieces, some into the sound waves of the pop. Eventually, all of this energy ends up as heat in the environment, slightly warming the kitchen air. The total amount of energy remains constant throughout all these transformations, a principle as fundamental as the conservation of mass or momentum. The irreversibility of popping demonstrates another deep principle of physics, the arrow of time imposed by the second law of thermodynamics. You can't unpop popcorn any more than you can unmix cream from coffee, or unburn a piece of wood. The popping process increases the entropy of the universe, spreading energy out, increasing disorder, moving the system toward equilibrium. Before popping, we had organized kernels with energy concentrated in chemical bonds and compressed moisture. After popping, we have disorganized, expanded corn with energy spread out as heat in the air. This increase in entropy is what gives time its direction, what makes the past different from the future, what drives all spontaneous processes in the universe. The way heat conducts through the oil and into the kernels illustrates Fourier's law of heat conduction, the same principle that governs heat flow through the Earth's crust, through the walls of our homes, through computer heat sinks, and through the tissues of our bodies. The rate of heat flow depends on the temperature difference, the thermal conductivity of the material, and the geometry of the system. Oil is a better conductor than air, which is why oil-popped corn heats more evenly than air-popped. The metal of the pot is an even better conductor, which is why kernels in direct contact with the pot bottom might scorch if the heat is too high. These same principles of heat conduction determine how quickly permafrost melts, how effectively insulation works, how animals regulate their body temperature. The pressure vessel created by each kernel's hull connects to a vast range of natural and engineered systems. The hull must withstand significant stress without failing prematurely, just like the walls of a submarine hull, the casing of a rocket engine, or the membrane of a living cell. The mathematics describing the stress in a popcorn hull, hoop stress, longitudinal stress, the influence of hull thickness and radius, are the same equations engineers use to design pressure vessels, pipes, and storage tanks. When a kernel's hull fails, it's experiencing the same kind of mechanical failure that engineers work to prevent in bridges, aircraft, and buildings. The crack propagation through the hull follows the same principles of fracture mechanics that apply to breaking glass, splitting wood, or tearing fabric. The foam structure of popped corn has implications beyond the kitchen. Foams are important in many applications: insulation, packaging, filtration, and even in understanding the large-scale structure of the universe, which some cosmologists describe as foam-like with galaxies forming along the walls of vast cosmic voids. The way starch forms a foam during popping is similar to how bread rises, how meringue is made, how volcanic pumice forms, how bone develops its porous structure. Understanding foam formation and stability is crucial for industries ranging from food processing to petroleum extraction to pharmaceutical manufacturing. The consistent popping temperature of corn connects to the broader concept of critical phenomena in physics. Many systems undergo dramatic changes at specific critical points. Water boils at 100 degrees Celsius at sea level. Iron loses its magnetism at 770 degrees Celsius. Helium becomes superfluid at 2.17 Kelvin. These critical points often mark boundaries between different phases or different behaviors of matter. The study of critical phenomena has revealed deep mathematical similarities between seemingly unrelated systems. The mathematics describing the critical point of water also describes magnetic phase transitions and even certain aspects of economic systems. Popcorn's critical popping temperature is a humble member of this family of critical phenomena that appear throughout nature. The optimization of popcorn through selective breeding illustrates how physical constraints shape biological evolution. Corn that pops well has been selected for a specific combination of traits: hull strength, moisture retention, starch composition, that work together to create the conditions for good popping. This is an example of how physics provides the rules within which evolution must work. Birds evolved wings that obey the laws of aerodynamics, fish evolved fins that follow the principles of fluid dynamics, and popcorn evolved kernels that respect the laws of thermodynamics and mechanics. Evolution is creative, but it cannot violate physical laws. It must work within the constraints imposed by physics, finding solutions that are both biologically viable and physically possible. The sound of popping corn connects to the physics of acoustics and wave propagation. The pop is a pressure wave travelling through air, following the same principles that govern all sound, from whispers to thunderclaps, from violin strings to volcanic explosions. The frequency of the pop, its loudness, its duration, all are determined by the physics of the popping process and the properties of air. Sound waves from popping kernels spread spherically outward, reflecting off the walls of our kitchen, interfering constructively and destructively to create the complex soundscape we hear. The same wave equations that describe these sound waves also describe electromagnetic waves, water waves, seismic waves, and even quantum probability waves. As we munch on our popcorn, feeling its crispy texture and tasting its toasted corn flavour, we're experiencing the results of Maillard reactions, the same chemical processes that brown bread crusts caramelize onions and create the complex flavours in roasted coffee. These reactions between amino acids and sugars are temperature dependent, which is why properly popped corn has a different flavour than raw kernels. The chemistry of these reactions is complex, producing hundreds of different compounds that contribute to flavour and aroma. The same types of reactions occur in our bodies, contributing to aging and various disease processes. Understanding Maillard reactions has implications for food science, medicine, and even the search for life on other planets, since these reactions might have played a role in the origin of life. The way we perceive the warmth of freshly popped corn involves heat transfer to our hands and mouths, nerve signals travelling to our brains, and the interpretation of these signals as the sensation of warmth. The thermoreceptors in our skin respond to temperature changes following the same physical principles that govern all molecular sensors. The neural signals travel as electrochemical waves, following the same cable equations that describe signal propagation in any conductor. The perception of temperature, like all perception, is our brain's interpretation of physical stimuli. A reminder that our experience of the world is always mediated by physics. The physics of light entering our eyes, sound waves reaching our ears, molecules binding to receptors in our nose and tongue, pressure and temperature affecting sensors in our skin. The efficiency of the popping process, how much of the heat energy actually goes into popping versus being lost to the environment, connects to fundamental limits on energy conversion set by thermodynamics. No process can be 100% efficient. Some energy is always lost as waste heat. This is why engines need cooling systems, why power plants need cooling towers, why our bodies generate heat even when we're at rest. The efficiency of popcorn popping is actually quite low. Most of the heat goes into warming the air, the pot, and the kitchen rather than into the actual popping process. But this inefficiency isn't a flaw, it's a fundamental consequence of the second law of thermodynamics, the same law that sets limits on the efficiency of car engines, power plants, and even biological processes. The transformation of hard kernels into light, fluffy popcorn represents a dramatic decrease in density. The same mass now occupies a much larger volume. This density change is similar to what happens in many natural and industrial processes. Water vapor is less dense than liquid water, which is why steam rises. Hot air is less dense than cold air, which drives convection currents in the atmosphere and oceans. The density changes in popping corn are more extreme than most phase changes, a 40 to 50-fold increase in volume, making it one of the most dramatic density transformations in common experience. This is why popcorn is such an efficient snack food from a satisfaction per weight perspective. A small amount of kernels produces a large volume of food. As we near the end of our freshly popped bowl, we can appreciate how this simple snack connects us to fundamental physical principles that operate throughout the universe. The laws governing popcorn are not special laws just for corn. They're the same laws that govern stars and atoms, weather and geology, biology and technology. In our kitchen, with our humble pot and our ordinary kernels, we've witnessed thermodynamics and phase transitions, pressure vessels and foam formation, critical phenomena, and irreversible processes. We've seen energy transform from electricity or gas to heat to mechanical work to sound. We've observed matter change state, entropy increase, and complex structures emerge from simple beginnings. Let us now slow everything down. Let us shrink ourselves in imagination until we can slip inside a single kernel of corn, drifting into that golden interior where one of nature's most sudden transformations is about to unfold. Close your eyes for a moment and picture yourself becoming smaller and smaller, passing through the tough outer hull as if it were the wall of a vast cathedral, entering into the starchy heart of the kernel where moisture hides in countless tiny pockets, where long chains of carbohydrates wind around each other like frozen rivers, where we can witness the slow build towards sudden change from the inside. Here, in this microscopic world, time seems to stretch and dilate, allowing us to observe processes that in the outer world flash by in fractions of seconds, but here unfold with dreamlike deliberation. The interior of our kernel is not uniform but layered, structured, organized in ways that reflect its biological origins and purpose. Near the hull, the starch is packed most densely, forming a protective barrier just inside the protective barrier of the pericarp itself. As we drift deeper toward the center, we encounter the flowery endosperm, softer and less densely packed, where the starch granules are surrounded by proteins and small amounts of oil. And at the very heart of the kernel lies the germ, the embryo that could have become a new corn plant if conditions had been different, rich with oils and proteins and the genetic information needed to create another generation. Each of these regions will respond differently to the heat that's beginning to penetrate from outside. Each will play its own role in the transformation to come. The starch molecules surrounding us are polymers, long chains of glucose units linked together in patterns that create different properties. Some chains are linear, forming what scientists call amylose, while others are highly branched, creating amylopectin. These molecules are currently in a semi-crystalline state, with regions of high order where the chains align perfectly, and regions of disorder where they tangle randomly. It's like being in a vast warehouse, where some sections are perfectly organized with everything in neat rows, while other areas are jumbled storage where things have been placed without pattern. This mixture of order and disorder is crucial for what's about to happen. Too much order and the kernel would be too rigid to expand properly, too much disorder and it wouldn't have the structural integrity to build pressure. The water molecules distributed throughout this starchy matrix are not free but bound, held in place by hydrogen bonds to the starch chains and to each other. At room temperature, they vibrate in place like prisoners rattling their cages, occasionally breaking free from one position only to be captured in another. But as heat begins to flow into our kernel from the surrounding oil, these water molecules begin to move more vigorously. Temperature, after all, is just a measure of molecular motion, and as the temperature rises, we can see and feel the increasing agitation of everything around us. The starch chains begin to flex and bend more dramatically, the water molecules dart about with increasing speed, and the entire structure starts to loosen and shift. At around 60 degrees Celsius, we begin to witness the process of gelatinization. Water molecules, now moving fast enough to break free from their positions more frequently, begin to penetrate into the ordered crystalline regions of the starch. They wedge themselves between the aligned chains, disrupting the perfect order, causing the starch granules to swell. It's like watching ice sculptures begin to melt, losing their sharp edges and defined shapes, becoming softer and more malleable. This process is essential for what's to come. Without gelatinization, the starch would remain rigid and brittle, unable to expand into the foam structure that characterizes popped corn. As the temperature continues to rise, passing 100 degrees Celsius, something remarkable begins to happen to the water molecules around us. Those with enough kinetic energy begin to escape from the liquid phase entirely, becoming vapor. But unlike water boiling in an open pot, these newly formed vapor molecules have nowhere to go. The tough hull of our kernel traps them, and so they begin to accumulate, building pressure. We can feel this pressure building around us, pressing in from all directions, compressing the remaining liquid water and the softening starch. It's like being deep underwater, where the pressure squeezes from every angle, except here the pressure is building rather than static. The mathematics of what's happening is elegant and precise. According to the ideal gas law, PV, nRT, as the temperature, T, increases, and the volume, V, remains constant, the pressure, P, must increase proportionally. But the water vapor in our kernel isn't quite an ideal gas. At these pressures and temperatures, the molecules interact with each other in ways that ideal gases don't. The actual pressure follows a more complex equation of state, but the basic relationship holds. Higher temperature means higher pressure when the volume can't change. We're inside a natural pressure cooker, a biological pressure vessel that's been optimized through thousands of years of selection to withstand remarkable forces. At 150 degrees Celsius, the pressure around us has reached perhaps 3 or 4 atmospheres. The remaining liquid water is superheated. heated above its normal boiling point but prevented from boiling by the pressure. The starch chains are now highly mobile, sliding past each other like wet noodles, held in place only by the constraining hull and the pressure pressing in from all sides. We can sense the tension building, the way the entire structure of the kernel is straining against its containment. It's like being inside a balloon that's being inflated toward its breaking point, feeling the material stretch and thin, knowing that eventually something must give. The hull above us, that tough biological pressure vessel, is experiencing stresses that would challenge many engineered materials. The cellulose fibers that make up the hull are arranged in layers, with fibers in each layer oriented differently from those in adjacent layers, creating a natural composite material with remarkable strength. But even these tough fibers have their limits. As the pressure builds, the molecular bonds holding the cellulose chains together begin to stretch. Somewhere in the hull, perhaps at a point where the fibers are slightly thinner, or where there's a microscopic flaw in the structure, the stress becomes too much. We've reached 170 degrees Celsius now, and something crucial happens to the starch around us. It passes through what materials scientists call the glass transition temperature, shifting from a hard, glassy state to a soft, rubbery state. This transition doesn't happen all at once throughout the kernel, but spreads like a wave from the hotter outer regions toward the cooler center. The starch that was rigid and brittle becomes stretchy and pliable, ready to expand, dramatically if given the chance. We're surrounded now by a strange kind of matter, not quite solid, not quite liquid, but something in between, a viscoelastic material that can flow like a thick liquid, but also stretch like rubber. The pressure has reached 6 atmospheres, maybe 7. Every square centimetre of the hull is experiencing a force of about 100 newtons, the weight of a 10-kilogram mass pressing outward. The water molecules around us are desperately trying to escape into vapour, held back only by the pressure and the constraining hull. The temperature gradients within the kernel create convection currents in the softened starch, slow swirls and eddies that distribute heat and maintain some mixing even in this confined space. We're at the edge of chaos, balanced on the knife edge between stability and explosive change. Time seems to slow even further as we approach the critical moment. In the outer world, this might last only a fraction of a second, but here in our miniature universe inside the kernel, we can observe each incremental change. The hull is stretching to its absolute limit, the molecular bonds straining, some beginning to break. The pressure is approaching the maximum the hull can withstand. The starch is in exactly the right state, soft enough to expand but with enough structure to form a stable foam. The water is superheated, ready to flash into steam the instant the pressure is released. Everything is poised, waiting, balanced at the threshold. We return again and again in our contemplation to this moment of balance, this edge between one state and another. It's a universal theme in nature, the moment before lightning strikes, the pause before an avalanche begins, the instant before a soap bubble bursts. These threshold moments contain a special kind of potential energy, not just physical but almost metaphysical, representing the boundary between what is and what could be. In our kernel, this threshold is defined by precise physical parameters, temperature, pressure, material properties, but it feels like something more, a held breath in the life of the kernel, a pause before transformation. The concept of thresholds appears everywhere in physics and in life. Water at degrees Celsius exists at the threshold between ice and liquid. A radioactive atom exists at the threshold of decay, possibly stable for billions of years or possibly decaying in the next instant. A star at the end of its life exists at the threshold of collapse, balanced between the outward pressure of fusion and the inward pull of gravity. And here, our kernel exists at the threshold of popping, balanced between containment and explosion, between order and chaos, between seed and snack. What makes this threshold particularly fascinating is its inevitability combined with its unpredictability. We know with absolute certainty that if we continue heating, the kernel will eventually pop. The laws of physics guarantee it. But we cannot predict the exact instant when it will happen. This combination of determinism and randomness is a fundamental feature of many physical systems. It appears in quantum mechanics, where we can predict probabilities but not individual events. It appears in chaos theory, where tiny differences in initial conditions lead to vastly different outcomes. and it appears here in our kernel, where the exact moment of popping depends on microscopic details we cannot fully observe or control. The threshold we're approaching is also a point of no return. Once the hull begins to fail, once that first crack appears and begins to propagate, there's no going back. The process will complete itself in milliseconds, transforming the kernel irrevocably. This irreversibility is a manifestation of the second law of thermodynamics, the law that gives time its arrow, that distinguishes past from future. We cannot unpop a kernel any more than we can reverse the flow of time itself. The threshold represents a one-way door through which our kernel must pass, leaving its original state behind forever. As we continue to drift through the superheated, pressurized interior of our kernel, we can appreciate the remarkable convergence of conditions required for successful popping. The temperature must be high enough to generate sufficient vapor pressure and to soften the starch, but not so high that the kernel burns. The moisture content must be enough to generate pressure, but not so much that the hull weakens prematurely. The hull must be strong enough to contain pressure, but weak enough to eventually fail. The starch must have the right composition to expand properly. All these requirements must be met simultaneously, creating a narrow window of conditions where popping can occur successfully. This convergence of requirements is what makes popcorn special among grains. Other grains lack one or more of these essential characteristics. Regular corn has too weak a hull to build sufficient pressure. Wheat and rice have the wrong kind of starch that doesn't expand properly. Sorghum can pop but requires different conditions and produces a different texture. Popcorn represents a unique solution to the challenge of creating an expanded grain product, a solution discovered by indigenous peoples of the Americas thousands of years ago and refined through selective breeding ever since. The waiting continues, the pressure builds, the temperature rises incrementally. We're now at perhaps 180 degrees Celsius, the temperature where most kernels pop. The hull is experiencing stresses near its breaking point. Somewhere, perhaps at a weak point we cannot see from our position inside the kernel, molecular bonds are beginning to fail. The crack hasn't started yet, but the conditions for its initiation are nearly complete. We're in that precious, precarious moment just before change, when all the necessary conditions have been met but the triggering event hasn't yet occurred. This is the moment of maximum potential, when all the energy that's been flowing into the kernel has been stored as pressure, as molecular motion, as stretched chemical bonds, waiting to be released. It's like a drawn bow just before the arrow is released, a compressed spring at maximum compression, a raised hammer about to fall. The energy is all there, ready to be transformed from potential to kinetic, from stored to released, from order to chaos. We float in this moment of suspension, this pause before action, this threshold between states. The beauty of this threshold moment is that it's both unique and universal. This particular kernel, with its specific size and shape and moisture content, will pop in its own unique way, creating its own particular pattern of expanded starch. But the physical processes governing this transformation are universal, the same in every kernel, in every pot of popcorn, everywhere in the universe where these conditions are met. We're witnessing both the particular and the general, the individual and the collective, the unique event and the universal law. As we prepare for the transformation that we know must come, we can reflect on the deeper meaning of thresholds in nature and in our own lives. Every change of state, every transformation, every growth from one stage to another involves passing through thresholds. Some are gradual, barely noticeable, like the slow transition from childhood to adulthood. Others are sudden and dramatic, like the popping of our kernel. But all involve this movement from one stable state through a period of instability to another stable state. The kernel teaches us that transformation often requires pressure, that change often comes suddenly after long preparation, that new forms emerge when old boundaries can no longer hold. The threshold also teaches us about the relationship between constraint and freedom. The hull of our kernel has been a constraint, trapping moisture and pressure, preventing the starch from expanding. But this constraint has been necessary for building the conditions for transformation. Without the hull's resistance, there would be no pressure buildup, no superheated water, no explosive expansion. The constraint creates the possibility for dramatic change. When the hull finally fails, the freedom will be sudden and complete, but it's a freedom that was made possible by the previous constraint. We sense that the moment is very close now. The pressure may have reached 7 or 8 atmospheres. The temperature is at the critical range. The hull is stretched to its limit. The starch is in the perfect state for expansion. The water is superheated and ready to flash to steam. All the conditions have aligned, all the requirements have been met, all the energy has been stored. We float here at the edge of change, in the last instant of the kernel's original form, in the pause before transformation, in the threshold between what was and what will be. This threshold moment connects our single kernel to the vast patterns of the universe. Stars exist at thresholds between burning and collapse. Atoms exist at thresholds between stability and decay. Ecosystems exist at thresholds between growth and decline. Civilizations exist at thresholds between order and chaos. And here, in our small kernel, we see these same patterns playing out in miniature. The threshold is not just a physical state, but a fundamental aspect of how change occurs in our universe, how new forms emerge from old, how energy flows and transforms, how time moves forward and never back. As we wait in this suspended moment, we can appreciate the profundity hidden in the ordinary. This kernel, this common snack food, this everyday transformation, contains within it lessons about pressure and phase changes, about thresholds and transformations, about constraint and freedom, about order and chaos. It's a reminder that the deepest truths of physics are not hidden in exotic locations or extreme conditions, but are present all around us, in our kitchens and gardens, in our daily experiences, in the simple act of making popcorn on a quiet evening. The moment is upon us now. Somewhere in the hull, perhaps just a few molecular layers away from where we float, the first bonds are beginning to break. The crack hasn't yet started its catastrophic propagation, but the initiation has begun. We're in the last microseconds of stability, the final instant before the dramatic change that will transform everything around us. The pressure is at its maximum, the temperature is at the critical point, the starch is ready to expand, the water is ready to become steam. Everything waits on the edge of transformation, balanced at the threshold, poised for the pop that must inevitably come. Let us now expand our view beyond the familiar yellow kernels in our pot, drifting gently into a wider world where other grains harbour their own secrets of transformation under heat. Picture, if you will, a quiet laboratory late at night, where patient researchers have arranged samples of different grains in small glass containers, each one waiting to reveal how it responds to the same conditions that make popcorn pop. There's sorghum with its smaller, rounder seeds, amaranth with its tiny pearl-like grains, rice in various forms from wild to cultivated, and even quinoa with its distinctive spiral germ wrapped around each seed. Each of these grains carries within it the same basic components as popcorn: starch, moisture, and some form of outer coating. Yet each behaves differently when heated, teaching us through their variations what makes popcorn's transformation so special. Sorghum, that ancient grain that has fed humanity for millennia, particularly in Africa and Asia, can indeed pop like popcorn, though its transformation is more modest, more restrained. When heated to similar temperatures as popcorn, around 175 to 190 degrees Celsius, sorghum kernels will expand to perhaps 2 or 3 times their original size, creating tiny white puffs that look like miniature popcorn. But the expansion is far less dramatic than corn's 40 to 50-fold increase in volume. The reason lies partly in the structure of sorghum's outer layer, which is thinner and more porous than popcorn's hull, unable to contain pressure to the same degree. The moisture escapes more gradually through tiny pores, preventing the explosive build-up that creates popcorn's dramatic transformation. It's like trying to inflate a balloon with small holes. You can create some expansion, but never the full, satisfying inflation of an intact balloon. Researchers studying sorghum popping have found that the grain starch composition also differs from popcorn in crucial ways. Sorghum starch has a different ratio of amylose to amylopectin, those 2 forms of starch polymers we encountered inside our popcorn kernel. This different ratio affects how the starch behaves when heated, how it gelatinizes, how it forms foam structures. The glass transition temperature is slightly different. The viscosity of the heated starch is different. The way it sets when cooled is different. These might seem like small distinctions, but they add up to create a fundamentally different popping behavior. Where popcorn creates large, irregular, crispy structures, sorghum creates small, uniform, slightly denser puffs. Amaranth presents an even more intriguing case study in grain popping. These tiny seeds, no bigger than poppy seeds, were a staple food of the Aztecs and are still important in many parts of the world. When heated on a hot surface, amaranth seeds will pop, but the process is so quick and the seeds so small that it's almost impossible to observe individual popping events. Instead, you get what seems like a simultaneous transformation of many seeds at once, creating a mass of tiny white expanded grains that stick together slightly, forming what in Mexico is called alegría, when mixed with honey or syrup. The popping temperature for amaranth is similar to popcorn, but the mechanism is subtly different. The key difference with amaranth is that its seeds are so small that heat penetrates to the center almost instantly. There's no significant temperature gradient from outside to inside as there is in larger grains. This means that the entire seed reaches the critical temperature almost simultaneously, and the moisture throughout the seed converts to vapor in a more uniform way. The seed coat of amaranth is also proportionally thinner than popcorn's hull, so it fails at lower pressures. The result is a gentler, less explosive pop that produces a more uniform expanded structure. Some researchers have speculated that if we could engineer corn kernels the size of amaranth seeds, they might pop in a similar way, though this remains untested. Rice presents a particularly interesting case because it can be made to pop, but only under specific conditions that differ from those used for popcorn. Regular milled rice, the white rice we find in grocery stores, has had its outer bran layer removed, leaving no strong container to hold pressure. When heated, it simply dries out and eventually burns. But unmilled rice, or rice that has been specially processed, can be made to puff or pop. In India, puffed rice called murmura, or mamra, is made by heating rice in hot sand, causing rapid expansion. The process works because the sand provides extremely rapid, uniform heating that causes the moisture in the rice to flash to steam before it can escape gradually. The physics of rice puffing reveals another important aspect of grain popping, the role of heat transfer rate. Popcorn pops well in oil because oil provides rapid, uniform heat transfer. Air-popped corn works but requires higher temperatures because air is a poor heat conductor. Sand, used for puffing rice, and sometimes for popping amaranth, provides excellent heat transfer because of the high contact area between the grains and the hot sand particles. Some researchers have experimented with other heat transfer media, salt, metal beads, even certain types of ceramic particles, finding that each creates slightly different popping or puffing characteristics. Wild rice, which isn't actually rice but rather the seed of an aquatic grass, behaves differently still. When heated, wild rice will eventually split open along its length, like a hot dog splitting on a grill, but it doesn't truly pop or puff. The structure of wild rice, with its elongated shape and longitudinal fibers, causes it to fail in a different mode than the more catastrophic failure of popcorn hulls. Instead of building pressure until explosive failure, wild rice tends to develop a crack that propagates slowly along its length, releasing pressure gradually. This is an example of what material scientists call ductile failure versus brittle failure. Wild rice deforms and splits, while popcorn shatters explosively. Quinoa, that nutritious pseudo-cereal from the Andes, has been the subject of recent research into alternative popped grains. Quinoa seeds have a unique structure with the germ wrapped around the outside of the seed in a spiral pattern. When heated, quinoa can be made to pop, but the expansion is minimal, and the texture is quite different from popcorn. The external germ tends to brown and become crispy, while the starchy interior expands only slightly. Some researchers have suggested that quinoa's popping behavior might be improved by breeding varieties with thicker seed coats or different starch compositions, but this work is still in early stages. Wheat and barley, two of humanity's most important grains, generally don't pop well, despite numerous attempts to develop popping varieties. The problem seems to be a combination of factors. Their seed coats are either too weak to build pressure or too tough to shatter properly. Their starch doesn't have the right properties for foam formation, and their moisture distribution isn't optimal for explosive expansion. However, both grains can be puffed using different processes, such as the gun puffing method used to make puffed wheat cereal, where grains are heated under pressure and then suddenly released to atmospheric pressure, causing expansion. This brings us to an interesting speculation about the future of popped grains. Could we engineer or breed grains specifically for popping? Could we create wheat that pops like popcorn, or rice that expands dramatically when heated? The answer is theoretically yes, but practically challenging. We would need to simultaneously modify multiple traits: seed coat, strength and brittleness, starch composition and behavior, moisture content and distribution, seed size and shape. Each of these traits is likely controlled by multiple genes, making traditional breeding slow and difficult. Genetic engineering might offer faster solutions, but would require detailed understanding of all the genes involved and how they interact. Some researchers have taken a different approach, looking not at modifying grains, but at modifying the popping process itself. What if we could coat regular grains with an artificial hull that would allow pressure buildup? What if we could inject moisture into grains in a way that optimizes pressure development? What if we could modify the starch structure through enzymatic treatment before popping? These approaches have shown some promise in laboratory settings, but none have yet produced results that match the simplicity and effectiveness of naturally popping corn. There's also interesting speculation about whether popping behavior might exist in grains we haven't yet discovered or haven't yet tested. There are thousands of grass species in the world, many producing seeds that have never been systematically tested for popping ability. In remote regions of the world, indigenous peoples might know of grains that pop but haven't shared this knowledge with the broader world. Some researchers have proposed systematic surveys of wild grasses, testing their seeds for popping ability, looking for new varieties that might have unique properties or nutritional advantages. The study of alternative popping grains has also led to insights about the evolution of popping ability. Why did some varieties of corn evolve the ability to pop while others didn't? Was it purely chance, or were there selective advantages to popping ability in nature? Some botanists have speculated that the ability to pop might have originally been a seed dispersal mechanism. Kernels that could explosively rupture might spread their contents further when exposed to fire, a common occurrence in many ecosystems. Others suggest that the tough hull of popping corn might have evolved as protection against insects or moisture, with popping ability being an accidental byproduct. Environmental factors also play a role in the popping ability of different grains. Grains grown in different climates, soils and conditions can have different popping characteristics even within the same variety. Popcorn grown in areas with consistent rainfall during the growing season tends to have more uniform moisture content and better popping quality. Corn grown in stressed conditions, drought, poor soil, pest pressure, might have thicker hulls or different starch properties that affect popping. This environmental influence adds another layer of complexity to understanding and optimizing grain popping. Recent research has also explored the nutritional implications of popping different grains. The high temperatures and rapid expansion involved in popping can affect the nutritional value of grains in complex ways. Some nutrients, particularly heat-sensitive vitamins, can be reduced, but other nutrients might become more bioavailable as cell walls are disrupted and starches are modified. The expansion process also reduces the density of the grain, which might affect satiety and consumption patterns. Some studies have suggested that popped grains might have a lower glycemic index than the same grains prepared in other ways, though results have been mixed and more research is needed. The economics of alternative popped grains is another area of speculation and research. Popcorn is successful, partly because it's economically efficient. A small amount of kernels produces a large volume of snack food with minimal processing. Could other popped grains achieve similar economics? Sorghum and amaranth are already commercially popped in some markets, but they remain niche products. The challenge is not just technical, but also cultural and economic. Consumers need to accept new products, supply chains need to be developed, and processing methods need to be optimized for commercial scale. There's also speculation about the role of popped grains in future food systems. As the world looks for sustainable, nutritious, and efficient food sources, popped grains might play an increasing role. They're shelf-stable, lightweight, and require no refrigeration. They can be made from whole grains with minimal processing and no additives. They provide dietary fiber and complex carbohydrates, in a form that many people find appealing. Some food futurists envision a world where a variety of popped grains, not just corn, become common snack foods and ingredients. The study of grain popping has also contributed to broader understanding of food material science. The principles learned from studying popping, how moisture and heat interact, how cellular structures respond to pressure, how biopolymers behave during rapid expansion, apply to many other food processes. This knowledge has been applied to developing new extruded snacks, improving baking processes, creating novel food textures, and even developing biodegradable packaging materials that use similar expansion principles. Looking at the variety of ways different grains respond to heat and pressure, we can appreciate the uniqueness of popcorn even more. The combination of traits that make corn pop so dramatically, the strong, moisture-proof hull, the right starch composition, the appropriate moisture content, the correct seed size, is rare in nature. It's a reminder that sometimes nature produces combinations that seem almost designed for human use, even though they evolved for entirely different reasons. Popcorn is one of these fortunate accidents, a grain that happens to transform in a way that humans find delightful. As we continue heating our various grain samples in our imagined laboratory, we can observe the subtle differences in how each responds. The sorghum pops with tiny, delicate sounds, like raindrops on leaves. The amaranth creates a soft rustling, like wind through grass. The rice, if specially prepared, puffs with a muffled expansion, like snow falling on snow. Each grain has its own voice, its own way of responding to heat and pressure, its own solution to the challenge of expanding under thermal stress. Together, they create a symphony of transformation, each playing its own part in the orchestra of heated grains. The exploration of alternative popping grains also raises philosophical questions about human food preferences. Why do we find popped textures appealing? Is it the contrast between the crispy exterior and airy interior? The way popped grains dissolve on the tongue? The satisfying crunch when we bite down? These preferences likely evolved over millennia of human food consumption, shaped by nutritional needs, food safety concerns, and cultural transmission. Understanding why we enjoy popped grains might help us develop new foods that satisfy these same preferences in novel ways. As this section of our contemplation draws toward a close, we can appreciate how the study of different grains and their popping behaviors illuminates the general principles we've been exploring. Each grain is a different experiment in the same physical processes: heat transfer, phase change, pressure buildup, structural failure, rapid expansion. By seeing how these processes play out differently in different grains, we gain a deeper understanding of the underlying physics. It's like listening to the same melody played on different instruments. Each version reveals different aspects of the musical structure. As we sit now in the gentle aftermath of popping, perhaps holding a warm handful of expanded kernels, feeling their impossible lightness against our palms, we can begin to draw connections between the physics we've witnessed and the deeper patterns of our own human experience. The threshold that each kernel crossed, that decisive moment between containment and release, between potential and transformation, mirrors countless thresholds in our own lives, moments when gradual change suddenly becomes dramatic transformation, when long preparation suddenly yields to rapid action, when we ourselves pop from one state of being into another. Think about your own breath for a moment, that gentle rhythm that continues whether you attend to it or not. Each breath represents a threshold crossing, a movement from the need for oxygen to its satisfaction, from the build-up of carbon dioxide to its release. The pressure in your lungs builds as your diaphragm contracts, creating a partial vacuum that draws air inward, then reverses as you exhale, pushing air back out into the world. This cycle of pressure and release, of filling and emptying, echoes the cycle we witnessed in our popping kernels. Your lungs, like the kernel hulls, are pressure vessels, constantly managing the balance between internal and external forces, constantly crossing the threshold between inhalation and exhalation. Consider how learning happens in our minds, not the gradual accumulation of facts, but those moments of sudden understanding when concepts that seemed separate suddenly connect, when patterns that were invisible suddenly become clear. These aha moments are like kernels popping in the landscape of our consciousness. We might study something for days, weeks, even years, building up pressure like heat slowly penetrating a kernel, and then suddenly, in an instant, understanding explodes into awareness. The preparation was gradual, but the realization is sudden. The knowledge was always there, like the moisture in the kernel, but it needed the right conditions, the right temperature of curiosity, the right pressure of necessity, to transform into insight. Our bodies themselves are constantly managing thresholds, maintaining what biologists call homeostasis through countless feedback loops and regulatory mechanisms. When our body temperature rises, we begin to sweat at a specific threshold. When our blood sugar drops, we feel hungry at a particular level. When carbon dioxide in our blood reaches a certain concentration, We feel the urge to breathe. These thresholds are as precise as the popping temperature of corn, calibrated through millions of years of evolution to keep us functioning within safe parameters. We are, in a sense, collections of thousands of thresholds, all carefully balanced, all constantly being approached and retreated from, crossed and recrossed. The question arises naturally: what does it mean that we can understand these thresholds, that we can describe them mathematically, predict them scientifically, and even manipulate them technologically? A kernel of corn knows nothing of temperature or pressure in any conscious sense, yet it responds perfectly to these physical parameters. We, on the other hand, can measure temperature, calculate pressure, understand the molecular basis of phase transitions, and still feel wonder when we watch kernels pop. This dual nature of our experience, being both subject to physical laws and capable of understanding them, places us in a unique position in the universe, at least as far as we know. Sleep itself, that state you may be approaching as you listen to these words, represents one of the most mysterious thresholds we cross regularly. The transition from wakefulness to sleep isn't gradual, even though drowsiness is. At some specific moment, consciousness shifts, brain waves change their patterns, and we cross from one state of being to another. Scientists can measure this transition, identifying the exact moment when someone falls asleep by monitoring electrical activity in the brain. Yet the subjective experience of this threshold remains elusive. We approach it every night, like kernels approaching their popping temperature, building up sleep pressure throughout the day until finally, at just the right moment, we pop from waking to sleeping. The thresholds in our emotional lives often follow patterns remarkably similar to those we see in popping corn. Anger builds like pressure in a kernel, sometimes releasing in a sudden outburst, sometimes dissipating gradually if it finds small outlets. Grief accumulates like heat, slowly penetrating our defenses until sometimes, suddenly, we break open in tears. Joy can build quietly and then burst forth in laughter. Love might develop slowly, imperceptibly, until one day we realize we've crossed a threshold and can never go back to not loving. These emotional transformations, like physical phase transitions, often involve a long build-up followed by a sudden change, a crossing of some invisible but very real boundary. Consider how decisions form in our minds, especially major life decisions. We might deliberate for months or years, weighing options, gathering information, building up evidence and emotion like heat building in a kernel. Then, often quite suddenly, we know what we must do. The decision crystallizes, the threshold is crossed, and what seemed impossible to decide becomes obvious and inevitable. This isn't so different from a kernel reaching its popping temperature. All the conditions gradually align until transformation becomes not just possible but necessary. Human development itself is marked by thresholds. A baby's first word comes after months of listening and babbling, then suddenly one day, intentional speech emerges. A child's first step follows months of strengthening muscles and developing balance, then in one moment, walking begins. Adolescence, despite its gradual physical changes, often feels like a series of sudden transformations, voice breaking, growth spurts, cognitive leaps. Even aging, that most gradual of processes, has its thresholds. The day we need reading glasses, the moment we realize we can't do something we once took for granted. The transition into new phases of life. Communities and societies also experience thresholds, moments when gradual changes suddenly cascade into transformation. Social movements build slowly, like heat spreading through a pot of kernels, until suddenly they pop into widespread awareness and action. Technologies develop incrementally for years or decades, then suddenly cross a threshold of adoption and change everything. Ideas spread slowly through populations until they reach a tipping point and suddenly seem to be everywhere. These collective thresholds follow the same statistical patterns we see in popping corn: a slow start, rapid acceleration, then gradual completion as the last holdouts finally transform or remain unchanged. The irreversibility of popping, the fact that we cannot unpop corn, mirrors the irreversibility of many human thresholds. We cannot unlearn what we have learned, unsee what we have seen, unfeel what we have felt. Each significant experience changes us in ways that cannot be undone, only built upon or integrated. Like the increased entropy of popped corn, our own complexity tends to increase over time. our internal structure becoming more elaborate, our patterns more intricate. This irreversibility is not a limitation but a gift. It's what allows us to grow, to develop, to become more than we were. What can we learn from the patience required for popping? The heat must build slowly, evenly, giving each kernel time to reach its threshold. Rushing the process by using too high a temperature produces burnt kernels and many unpopped ones. Similarly, in our own lives, transformation often requires patience, steady application of effort, and the right conditions maintained over time. We cannot force insight, rush healing, or accelerate growth beyond its natural pace. Like the steady heat under a pot of kernels, consistent, patient effort often produces better results than intense but brief attempts at change. The variation we see in popping, some kernels popping early, most in the middle, some late, and some never, reflects the variation we see in human development and achievement. In any group of people learning a new skill, some will grasp it quickly, most will learn at an average pace, some will take longer, and some may never quite get it. This isn't a flaw in the system, but a natural consequence of individual variation. Just as each kernel has slightly different properties that affect when it pops, each person has unique characteristics that affect how they respond to life's pressures and opportunities. The communal aspect of popping, the way kernels seem to pop together, even though each is responding individually, mirrors how humans often change together even while experiencing individual transformations. In a classroom where learning is happening, individual insights seem to cascade through the group. In a family going through change, members often transform in related ways at similar times. In societies experiencing upheaval, individuals making personal decisions create collective transformation. We are separate kernels in the same pot, each responding to our own internal pressures, yet creating patterns together. The sound of popping corn, that cheerful, almost celebratory noise, reminds us that transformation, even when violent at the microscopic level, can be joyful at the human scale. The breaking of old structures to create new ones, the release of confined energy, the expansion into new forms, these can be causes for celebration rather than mourning. Not all breaking is breakdown. Sometimes it's breakthrough. Not all explosion is destruction. Sometimes it's expansion. The pop of a kernel is a tiny celebration of successful transformation, a small applause for change achieved. As we sit with our bowl of popped corn, we can reflect on the thresholds we've crossed to arrive at this moment in our lives. Each of us has experienced countless transformations, physical, mental, emotional, spiritual. We've built up pressure and released it, absorbed heat and radiated it, approached critical points and passed through them. We are, in a sense, the sum of all our popped moments, all our crossed thresholds, all our transformations from one state to another. Yet unlike popped corn, we retain the capacity for further transformation, further growth, further popping into new forms we cannot yet imagine. The ability to recognize and work with thresholds is perhaps one of humanity's greatest skills. We've learned to identify the signs that change is approaching, in ourselves, in others, in systems and societies. We've developed practices like meditation, therapy, education, and art that help us navigate thresholds more skillfully. We've created rituals and ceremonies to mark threshold crossings, birthdays, graduations, weddings, funerals, acknowledging their importance in the rhythm of human life. We've built entire philosophies and religions around the concept of transformation, recognizing it as central to the human experience. Yet for all our sophistication in dealing with thresholds, we remain subject to the same physical laws as popping corn. We cannot skip the build-up phase and jump straight to transformation. We cannot avoid the irreversibility of change. We cannot control exactly when or how thresholds will be crossed. This limitation is also a gift. It means transformation remains somewhat mysterious, somewhat magical, somewhat beyond our complete control. Like the kernels in our pot, we can create the right conditions for change, but the exact moment and nature of transformation retains an element of surprise. The warmth of the popped corn in our hands connects us to the warmth of human connection, the heat of passion and purpose that drives transformation in our lives. Just as heat from the stove transformed the kernels, the warmth of love, curiosity, creativity, and connection transforms us. We are both the kernel and the heat source, both the transformed and the transformer, both the subject and the object of change. This recursive relationship, Our ability to observe and influence our own transformations adds layers of complexity that go far beyond the simple physics of popping corn. Yet the fundamental patterns remain recognizable. As we continue to contemplate these connections between popping, corn and human experience, we might notice that the very act of contemplation is itself a kind of threshold phenomenon. Thoughts build up gradually, connections form slowly, then suddenly, understanding crystallizes. The meditation on popcorn becomes a meditation on existence. The observation of physical processes becomes insight into life processes. The simple becomes profound through patient attention. We are crossing thresholds even as we think about thresholds, transforming even as we contemplate transformation. The kitchen has grown quieter now, the excitement of popping replaced by a gentle stillness that wraps around us like a comfortable blanket, and we find ourselves in that peaceful aftermath where transformation has completed its work and left us with something new, something expanded, something that bears little resemblance to what we started with, yet carries within it the essence of what was. The last echoes of popping have faded into memory, leaving only the soft presence of completed change, the evidence of physics made edible, of laws made tangible, of the universe's rules expressed in the simple form of a snack that sits before us, cooling slowly, releasing the last wisps of its steam into the evening air. Let us take this moment to gently revisit the journey we've travelled together, not to memorize or to study, but simply to let the ideas settle into that comfortable place where knowledge becomes feeling, where understanding becomes intuition, where facts transform into a kind of wisdom that needs no words. We began with a simple question: why does popcorn pop at around the same temperature? And found ourselves exploring the deepest patterns of physical law, the mathematics of collective behavior, the poetry of phase transitions, the philosophy of thresholds and transformation. Each kernel that popped was a teacher, each sound a lesson, each expanded piece of corn a small demonstration of principles that govern everything, from the smallest particle to the largest galaxy. The temperature at which popcorn pops, that narrow range around 180 degrees Celsius, no longer seems arbitrary but inevitable, the result of a beautiful confluence of factors that had to align just so. The strength of the hull evolved over millennia to protect the seed yet fail at just the right pressure. The moisture content preserved at just the right percentage to generate sufficient steam without weakening the structure. The composition of the starch, perfectly suited to transform from hard crystal to soft foam at precisely the temperature where pressure peaks. These factors didn't conspire to create perfect popping. Rather, human selection found and refined this natural accident, this fortunate combination of traits that happened to produce something delightful. Perhaps it's enough now to simply appreciate this convergence without needing to hold all the details in our conscious minds. The Clausius-Clapeyron equation can fade into the background, its mathematical precision dissolving into a general sense that pressure and temperature dance together in predictable ways. The glass transition temperature can become simply the idea that things change state when conditions are right. The statistics of normal distributions can settle into an understanding that variation is natural, that not everything happens at once, that patterns emerge from many individual events, each following their own timeline. The kernels that never popped, those few that remain at the bottom of our pot, unchanged despite all the heat and opportunity, remind us that transformation is never universal, never complete, never without its exceptions. And perhaps that's as it should be. Perhaps the unpopped kernels serve their own purpose, reminding us that not everything must change, that resistance to transformation is also a valid response, that maintaining form in the face of pressure is its own kind of strength. They are not failures, but simply followers of a different path, responding to the same forces but with different results, like people who remain themselves despite all pressures to change. As the evening deepens and our contemplation continues its slow spiral toward rest, we can feel how the questions we've explored begin to soften, their sharp edges of curiosity becoming rounded with satisfaction. Not because we've answered everything, but because we've asked deeply, looked carefully, wondered genuinely. The mystery of popcorn has not been solved so much as appreciated, not conquered, but befriended. We know more than when we started, yet the knowing has only deepened the wonder, only made the ordinary seem more magical, not less. The cooling popcorn before us continues its journey through temperature and time, each piece slowly equilibrating with its surroundings, releasing its heat to the air molecule by molecule, photon by photon, in a process that will continue until everything reaches the same temperature, the same state of thermal equilibrium that all things seek. This cooling is as much a part of the story as the heating and popping, the return to stillness as important as the moment of transformation. Energy that was concentrated is now dispersing. Order that was created is now slowly relaxing toward disorder. Yet the forms created in that moment of popping remain, frozen in their expanded state, monuments to the transformation they underwent. You don't need to remember the specific pressure at which kernels pop, or the exact mechanism of starch gelatinization, or the mathematical relationship between temperature and vapor pressure. These details can drift away like steam from hot popcorn, leaving behind only a general sense of understanding, a feeling for how things work, an intuition about the patterns that govern change. What matters is not the facts, but the feeling, not the data, but the deeper appreciation for the elegant ways in which simple rules create complex behaviors, simple ingredients create satisfying snacks, simple questions lead to profound contemplations. The rhythm of our exploration has been slowing gradually, like the decreasing frequency of pops as the kernels completed their transformation. Where once our thoughts raced to keep up with rapid changes and sudden revelations, now they move with the measured pace of deep breathing, the gentle rhythm of a resting heart, the slow cycles of mind preparing for sleep. This deceleration is natural, necessary, part of the same pattern we've been observing: build up, release, return to equilibrium. Our mental energy, like the heat in our popcorn, is dissipating into the peaceful darkness, finding its own level, its own rest. Consider how far we've travelled from that first moment when we stood together in the kitchen, pot in hand, kernels waiting. We've journeyed to the interior of kernels, to laboratories where scientists peer into the mysteries of grain behaviour, to the vast patterns of physics that govern all matter and energy. We've connected the pop of corn to the breath in our lungs, the thoughts in our minds, the transformations in our lives. We've seen how individual events create collective patterns, how simple rules generate complex behaviours, how patience and proper conditions enable transformation. And now, as our journey nears its end, we can let all of this simply be, simply rest in our awareness without effort or strain. The questions we've asked don't require final answers tonight. Why does popcorn pop at around the same temperature? We've explored this from many angles, through many lenses, with many metaphors and explanations. But ultimately, perhaps the most satisfying answer is simply, because that's how the universe works at this scale, with these materials, under these conditions. The laws of physics, neither cruel nor kind but simply consistent, create the conditions where kernels can transform into popcorn, where seeds can become food, where the ordinary can become extraordinary through the application of something as simple as heat. Let the complexities we've explored begin to blur now, like the softening of focus that comes as eyes grow heavy. The sharp distinctions between phases can become gentle gradients. The precise measurements can become general impressions. The scientific terminology can dissolve back into everyday language. What remains is not less true for being less precise. Sometimes the soft focus understanding that comes with drowsiness is more true to the feeling of things than the sharp-edged clarity of full wakefulness. In this gentle state between knowing and not knowing, between consciousness and sleep, we might find a different kind of understanding, one that needs no words or equations. The popcorn continues to cool, each piece a small sculpture created by physics, a tiny monument to the transformation of matter under energy's influence. Some pieces are perfectly formed, others wildly irregular. Some expanded fully, others only, partially. Each one is unique, yet all share the common experience of having passed through the threshold from kernel to popcorn. They sit now in their bowl or pot, no longer changing, no longer transforming, simply existing in their new state, patient and still in the darkness of the kitchen. You're free now to let your attention drift away from the details of our exploration, to let the specific facts and figures fade like the last heat from the cooling kernels. What matters is not that you remember everything, but that you've spent this time in gentle contemplation of the everyday magic that surrounds us. The universe continues its work whether we observe it or not, whether we understand it or not, whether we're awake or asleep. Kernels will continue to pop at around the same temperature tomorrow and the next day, and for as long as humans continue to apply heat to corn, following the same laws with the same patient consistency. The questions can rest now, like seeds planted in the soil of consciousness, not needing immediate answers or resolution. Why does popcorn pop at around the same temperature? The question itself has become a friend, a companion through this evening's journey, a doorway into wonder that need not be closed just because we've walked through it. Questions, like kernels, carry potential within them, and sometimes it's enough to simply appreciate that potential without needing to force it to manifest. Some questions pop into answers quickly, others slowly, and some remain forever as questions, and that's perfectly fine. As you settle deeper into rest, perhaps you can still hear, very faintly, the echo of popping corn, not the actual sound but the memory of it, the impression it left in consciousness. It was a cheerful sound, a celebratory sound, a sound that spoke of successful transformation and energy released. Now in the quiet that follows, we have a different kind of sound, the sound of completion, of rest, of systems returning to equilibrium. This too is part of the physics we've explored, this tendency toward balance, toward stability, toward the peaceful state where all forces are balanced and nothing needs to change. The journey from kernel to popcorn has been our teacher tonight, showing us through simple example how the universe works at scales we can see and touch and taste. But now the teaching is complete, the lesson has been given, and we're free to simply rest in whatever understanding has come, without needing to grasp or hold or remember. Like the heat that flowed from stove to kernel and now dissipates into the night, our mental energy can flow outward, spreading thin, finding rest in the vast quietness that surrounds us. Perhaps tomorrow you'll make popcorn again, or perhaps not for days or weeks or months, but whenever you do, you might find that you hear it differently, see it differently, understand it differently, not because you'll remember all the details we've explored, but because you've spent this time in deep contemplation of its nature. You've looked beneath the surface of the ordinary and found the extraordinary. You've asked why and received not a simple answer, but a rich tapestry of interconnected explanations that reveal the deep patterns of physical law. The temperature remains important, those 180 degrees Celsius that mark the threshold of transformation. But now it's not just a number, but a gateway, a critical point where multiple processes converge to create change. The moisture content remains crucial, that 13 to 14% that provides just enough steam, but now it's not just a percentage but a balance point between too little and too much. The hull strength remains essential, strong enough to build pressure but weak enough to eventually fail. But now it's not just a material property, but a demonstration of how constraints enable transformation. All of these factors, all of these details, all of these explanations can now settle like sediment in still water, forming layers of understanding that don't need to be stirred up or examined, simply allowed to rest where they've fallen. The conscious mind can release its grip on the facts and let them sink into deeper places where they might inform intuition, enrich perception, and add depth to experience without ever needing to be explicitly recalled. This is how deep learning happens, not through memorization but through contemplation, not through grasping but through gentle attention that allows understanding to settle naturally into place. And so we arrive at the end of our journey, though in truth there are no real endings in the universe, only transformations, only changes of state, only movements from one form of being to another. And here in the quietness of our kitchen, with the stove now cool and the last kernel long since popped, or accepted its fate as one that would not transform tonight, we can feel ourselves held in the vast gentleness of physical law that governs all things with perfect consistency and no judgment, no preference, no urgency, only the patient unfolding of cause and effect that has been happening since the universe began and will continue until time itself transforms into something we cannot yet imagine. The bowl of popcorn sits before us now, completely still, completely at rest. Yet even in this stillness, motion continues at scales too small for us to perceive, molecules vibrating with thermal energy, electrons orbiting nuclei, quantum fields fluctuating in the vacuum between particles. The popcorn that seems so solid, so stable, so unchanging, is actually a dynamic system in equilibrium, a constant dance of forces and particles that creates the illusion of stillness through balance rather than absence of motion. This is the deep truth of matter. What seems solid is mostly empty space. What seems still is constantly moving. What seems permanent is always slowly changing. Each piece of popped corn in our bowl is like a small galaxy with its own structure, its own history, its own unique pattern of expansion frozen in time. The starch molecules that form its structure are themselves made of carbon, hydrogen, and oxygen atoms that have existed since long before Earth formed. The carbon was forged in the cores of stars that lived and died billions of years ago, scattered their enriched guts across space in supernovae, and eventually coalesced into our solar system, our planet, our biosphere, and finally into the corn plant that produced these kernels. When we eat popcorn, we are literally consuming stardust, taking into our bodies atoms that have travelled across cosmic distances and through cosmic time to arrive in this moment, in this form, in this quiet kitchen. The hydrogen in the moisture that created the steam for popping is even older, created in the first few minutes after the Big Bang when the universe was hot enough for nuclear fusion, but cool enough for protons to be stable. These primordial hydrogen atoms have been cycling through stars and planets, oceans and clouds, living beings and geological formations for nearly 14 billion years. They've been part of ancient seas, prehistoric organisms, countless cycles of evaporation and precipitation, and now they've participated in the small explosion of a popping kernel, continuing their endless journey through different forms and configurations. The energy that heated our kernels came ultimately from the sun, that local star that maintains its own critical balance between the outward pressure of fusion and the inward pull of gravity. The sunlight that grew the corn, captured through photosynthesis and stored in chemical bonds, has been released and transformed multiple times, from light to chemical energy, to heat to mechanical work to heat again, following the great circulation of energy that powers all life and most geological processes on Earth. Even if we used electricity to heat our popcorn, that energy likely came from ancient sunlight stored in fossil fuels, or from current sunlight captured by solar panels, or from the motion of water driven by solar-powered evaporation, or perhaps from the nuclear forces that also power the sun, harnessed in nuclear reactors. The laws that govern the popping of our corn are the same laws that govern the formation of galaxies, the birth of stars, the evolution of life, the firing of neurons in our brains as we contemplate these connections. There is no separate physics for popcorn, no special rules for kernels, no exemptions or exceptions. The same thermodynamics that builds pressure in a kernel builds pressure in stellar cores. The same phase transitions that transform water to steam in corn transform hydrogen to helium in stars. The same statistical mechanics that creates the bell curve of popping times creates the distribution of stellar masses, planetary orbits, and molecular velocities. We are small, temporary arrangements of matter and energy in a vast universe that operates on scales we can barely comprehend, yet somehow we're able to observe, understand, and appreciate the patterns that govern everything from quarks to quasars. The fact that we can ask why popcorn pops at a certain temperature and actually find meaningful answers connects us to something profound about the nature of existence. We are the universe becoming aware of itself, matter contemplating matter, patterns recognizing patterns. In our quiet kitchen, making our simple snack, we participate in the cosmic endeavor of consciousness, examining the very laws that create and sustain consciousness. The popcorn teaches us about more than just physics. It teaches us about the beauty of constraint and release, the necessity of pressure for transformation, the value of patience in creating conditions for change. Each kernel that popped had to experience confinement before it could expand, had to build up internal pressure before it could release, had to reach a crisis before it could transform. This pattern appears everywhere in nature and in our lives. The compression that precedes explosion, the struggle that precedes breakthrough, the darkness before dawn. The universe seems to favour this pattern of gradual build-up followed by sudden release, whether in popping corn, earthquakes, evolution, or insight. As you drift towards sleep, perhaps still hearing the faint echo of popping in your memory, you remain connected to all of this, to the vast cosmos and its patient laws, to the long history of matter and energy that led to this moment, to the future transformations that await the atoms currently arranged as your body and consciousness. You're not separate from the physics we've explored, but an expression of it, not an observer of the universe, but a participant in it, not outside the laws of nature, but a beautiful example of what those laws can create when given sufficient time and the right conditions. The kernel that became popcorn has completed its transformation for now, but its atoms will continue their journey. Perhaps tomorrow the popcorn will be eaten, its starches broken down into sugars, its sugars metabolized into energy and carbon dioxide, its atoms incorporated into human bodies, or exhaled into the atmosphere to be captured again by plants and built into new kernels. Or perhaps some will be discarded, decomposed by bacteria and fungi, returned to soil to nourish future growth. The atoms are immortal even as the forms they create are temporary, and in this endless recycling of matter and energy, we see the true continuity of existence. The question we began with, why does popcorn pop at around the same temperature, has led us through physics and chemistry, through cosmology and philosophy, through the microscopic and the cosmic, through the practical and the profound. We've found that simple questions, deeply pursued, reveal the interconnectedness of all things, the unity of physical law, the elegance of nature's solutions to the challenges of existence. The temperature at which popcorn pops is not arbitrary but necessary, not isolated but connected to everything else, not mundane but miraculous when seen with patient attention and gentle wonder. In the darkness of the kitchen now, with perhaps only the faint light of stars through a window or the gentle glow of a clock marking time's passage, the popcorn sits in perfect stillness, no longer transforming, no longer changing, simply existing in its expanded state. It has found its new equilibrium, its new form, its new way of being in the world. It cannot return to being kernels, cannot undo its transformation, cannot reverse the arrow of time that carried it from potential to actual, from seed to snack, from order to a higher form of disorder that we happen to find delicious. You too are finding your equilibrium now, that peaceful state between waking and sleeping where thoughts slow and soften, where the boundaries between self and world become gentle and permeable, where consciousness prepares for its nightly transformation into dreams and deep sleep. The questions about popcorn can rest now, answered not with finality but with appreciation, understood not completely but sufficiently, explored not exhaustively but lovingly. The universe will continue its patient work while you sleep, maintaining the laws that keep atoms stable and planets in orbit, continuing the heat flow that drives weather and ocean currents, sustaining the quantum fields that underlie all matter and energy. Tomorrow, somewhere in the world, someone will heat kernels of corn to around 180 degrees Celsius, and they will pop just as they have for thousands of years, just as they did tonight in our contemplation, just as they will for as long as humans continue this simple act of transformation. Each popping will be unique in its details but identical in its physics, individual in expression but universal in principle. The sound of popping corn will continue to bring small joy to kitchens and movie theatres, to festivals and quiet evenings at home, a humble reminder that transformation can be both dramatic and delightful, both violent and nourishing, both irreversible and necessary. As consciousness fades towards sleep, as your breathing deepens and slows, as your muscles release their last tension and settle into rest, you remain part of this vast, gentle universe that operates by consistent laws and creates endless variety within those laws. You're made of the same stuff as the popcorn, governed by the same forces, participating in the same grand experiment of matter, organizing itself into ever more complex and beautiful forms. The warmth you feel is the same warmth that popped the corn. The breath you breathe contains atoms that have been part of countless other beings and objects. The thoughts that drift through your awareness are patterns in the same electromagnetic fields that carry light from stars to Earth. And so, as you drift into sleep, you remain part of this quiet universe, wrapped in its laws, carried by its mysteries, gently, peacefully, into the night where dreams transform experience into new patterns, where consciousness rests and regenerates, where you continue to exist within the vast web of cause and effect that connects popcorn to galaxies, kernels to consciousness, simple questions to profound understanding. The popcorn has finished its popping, the contemplation has reached its natural end, and you are free to rest in the knowledge that the universe continues its patient work, whether you observe it or not, whether you understand it or not, whether you are awake or deeply, peacefully asleep. In this final moment of our journey together, as the last words fade into silence and the last thoughts dissolve into the quietness of approaching sleep, we can appreciate the perfect appropriateness of ending where we began, with wonder at the ordinary, with curiosity about the everyday, with gentle attention to the small miracles that surround us always. The popcorn sits in its bowl, complete in its transformation. The kitchen rests in darkness, its role as laboratory and classroom finished for tonight, and you, having travelled through physics and philosophy, through microscopic observation and cosmic connection, through questions and contemplations, can now rest in the simple, profound truth that everything is connected, everything follows the same laws, everything participates in the same magnificent unfolding of possibility into actuality, of potential into form, of kernels into popcorn, of curiosity into understanding, of wakefulness into sleep. The universe continues its gentle work, and you, wrapped in its consistent laws and carried by its patient processes, drift peacefully into the night, into rest, into dreams. Still part of the same physics that makes kernels pop, still subject to the same beautiful constraints and possibilities, still participating in the endless transformation of matter and energy that began with the Big Bang and continues in every moment, in every breath, in every heartbeat, in every thought, and in every kernel of corn that reaches its critical temperature and transforms suddenly and irreversibly into something new, something expanded, something that feeds and delights and reminds us that even the simplest things, when examined with patient attention, reveal the profound patterns that connect all things in this vast, gentle, endlessly creative universe.